Hello there and welcome to Science for Sleep, where curiosity finds a quiet corner and science takes its time, never rushing, always meandering toward a place of calm. Tonight we're going to drift together through one of the biggest questions the human mind has ever tried to hold. How will the universe end? It feels almost impossible to imagine something as vast as everything having an ending. Yet for as long as people have looked at the stars, we've wondered not only where it all began, but also what the final page of the story might look like. Will it fade quietly like a candle, collapse back into itself, or break apart in some spectacular display? It's a question filled with possibilities, each one stranger and grander than the last. And yet, even as we explore these scientific ideas, we're still just people lying under the night sky, asking questions as old as wonder itself. Before we begin, let me ask you something simple. Where are you listening from tonight? Maybe you're curled up in bed, maybe you're sitting in a chair winding down, or maybe you're half asleep already, letting these words wash over you. Wherever you are, the same stars that light up your sky are part of this story too. The atoms in your body, the light in your eyes, all of it will share the universe's fate, however far away it might be. That thought alone can be strangely comforting, knowing we're not apart from the cosmos but woven into it. And if you find yourself enjoying this journey, if the quiet pace and the gentle exploration bring you a little rest, I'd be grateful if you liked this video or subscribed. It helps others who may be searching for a moment of calm to find their way here too. Now, let's take a slow breath together, loosen the hold of the day, and begin our long walk into the future of everything. When people ask about the end of the universe, they often imagine something dramatic, like a final explosion or a great collapse. But the truth is that the story is bigger and more gradual than any single moment. The universe is not a small play with a quick curtain drop. It is a theatre so vast that even its endings take more time than we can fully grasp. Imagine the longest timescale you can think of, then multiply it again and again, stretching out into numbers so enormous that they lose all meaning in daily life. That's the canvas on which the fate of the universe is painted. Billions of years, trillions, and then numbers beyond ordinary language. Trying to hold those scales in mind is a bit like trying to count grains of sand on every beach on Earth, not once, but countless times over. Scientists often talk about cosmic endings in terms of possibilities, and these possibilities depend on the rules of physics. Rules that seem unshakable, yet leave room for mysteries we're still trying to understand. Some ideas focus on the universe slowing down and cooling until everything grows dark. Others imagine the fabric of space stretching so far that even the smallest particles are torn apart. There are theories where the universe might reverse direction, folding back into a dense hot point, or cycles where everything begins anew after every ending. Each possibility feels different, yet all are united by the same question. A question as much about beginnings as it is about endings. To understand any of this, it helps to think about what the universe actually is. When we say the universe, we're talking about everything, all the stars and galaxies, the vast voids between them, the dark matter we can't see, and the energy that seems to push space apart. It's not just a place filled with things, it is space itself, the fabric in which those things exist, and the laws that govern how they move. So when we ask how it all ends, we're not asking about just stars or planets or even life. We're asking what happens to existence itself, to time and space, to matter and energy in their most basic forms. This might sound overwhelming, but we can take it slowly, one step at a time, the way you might trace your finger along a winding path. The first step is to look at the universe as it is now. Observations show us that space is expanding. Galaxies are not fixed in place like lights in a room. They're drifting apart as the space between them stretches. This discovery, first made in the early 20th century, completely changed how we think about the cosmos. If galaxies are moving apart today, that means in the past they were closer together. Follow that backward far enough, and you reach a moment when everything we see now was packed into an unimaginably hot and dense state. That's the idea of the Big Bang. Not an explosion in space, but an expansion of space itself. From that beginning, the universe has been growing and cooling for nearly 14 billion years. The expansion is not just continuing, it's accelerating. Something we call dark energy seems to be pushing space outward faster and faster. The exact nature of dark energy remains one of the biggest puzzles in science. But its effect is clear. Galaxies far away are rushing off at speeds we can barely imagine, and the farther they are, the faster they go. It's as if the universe is not only expanding, but doing so with increasing urgency. And that acceleration matters deeply for the question of endings. Because whether the universe slows down, stops, reverses, or races outward forever depends on how this expansion behaves. For most of human history, people imagine the cosmos as eternal, steady, unchanging. But now we know it has a history, and like all things with a beginning, it may also have an end. That realization can be both unsettling and oddly reassuring. On one hand, it makes the universe feel fragile, like something that can vanish. On the other, it connects us more deeply to its story. Because if the universe has a lifetime, then our own lifetimes, however short by comparison, are part of a much larger rhythm. One way to think about the ultimate fate is to look at energy. Energy drives everything. Stars burn because nuclear reactions release energy. Galaxies shine because billions of stars are radiating light. Even life itself depends on the flow of energy, from sunlight to food to movement. But energy is not infinite. Over time, it spreads out. It disperses. According to the laws of thermodynamics, disorder increases and energy available for work decreases. This gradual slide toward balance is called entropy, and entropy plays a starring role in many theories about how the universe will end. Imagine a hot cup of tea in a cool room. At first the tea is warm, giving off steam, radiating heat, but left alone, the tea cools until eventually it reaches the same temperature as the room. At that point, no more change happens. There's no energy difference left to drive it. Now stretch that simple idea to the entire universe. Over vast spans of time, stars will burn out, galaxies will dim, and matter itself may fall apart into simpler and simpler particles. Energy will spread thinner and thinner until there are no differences left to power change. That is the idea of heat death, one of the most widely discussed scenarios for the universe's fate. But heat death is only one path, and not the only one scientists consider. Another possibility is that the expansion of the universe might one day slow down and reverse. Instead of galaxies rushing apart, they could begin falling back together. Over unimaginable timescales, everything could collapse into a dense state once again, leading to what's called the Big Crunch. From there, who knows? Some suggest a new expansion could begin, making the universe cyclical, with endless repeats of birth, growth, and collapse. Others see it as a final end, a return to the conditions from which everything began. And then there's the scenario with perhaps the most dramatic name, the Big Rip. If dark energy is not constant but grows stronger over time, then eventually it could overwhelm every force in the universe. First, it would pull apart galaxies, then stars, then planets, and finally even atoms themselves. Everything would be shredded by the relentless expansion of space. It's a scenario both terrifying and fascinating, though highly dependent on the true nature of dark energy, which we still don't fully understand. Each of these possibilities, the slow fade of heat death, the collapse of the Big Crunch, the violent tearing of the Big Rip, paints a different picture of the end. And yet, in every picture, there is a sense of inevitability. The universe is not static. It is changing, evolving, moving. Whether it ends in silence, fire, or something stranger, it will not remain as it is forever. Thinking about these endings can stir up many feelings. Some people find it frightening, the idea that everything we know will one day vanish. Others find it calming, a reminder that even the largest things in existence are part of cycles beyond our control. For me, I find a strange comfort in knowing that the universe is a story, and like all stories, it has arcs, turning points, and eventually conclusions. We may not be around to see those distant chapters, but we can still wonder about them now, sitting here in the present, listening quietly as the night deepens. The universe's story of endings can't really be told without first talking about stars, because in many ways they were the first clocks, the first makers of change, the first reminders that time was moving at all. Long before humans invented sundials, before we built atomic clocks or drew calendars on stone, the stars were there. They burned, they flickered, they rose and set, and even though early people didn't know the physics behind them, they sensed that these shining points were more than decoration. They were the heartbeat of the cosmos. To understand where the universe is going, we have to understand how stars live, how they die, and how in dying they shape the next stages of everything. It's worth pausing for a moment to imagine the earlier stars, not the ones you see above your head tonight, but the very first ones that formed in the newborn universe. At the start, there wasn't much variety. After the Big Bang, the cosmos was mostly hydrogen and helium, with a tiny trace of lithium. There were no heavy elements, no carbon, no oxygen, nothing that could make rocks or water or people, just simple gas filling space. Gravity, though, never rests. Slowly, under its pull, these gases began to gather into clumps, and as the clumps grew, they pulled in even more matter. Over millions of years, these gatherings became dense enough that the atoms inside were squeezed to incredible pressures and temperatures. At some point, the squeeze became so intense that hydrogen nuclei began to fuse into helium, releasing energy in the process. That was the birth of the first stars, called Population 3 stars by astronomers. These stars were nothing like the Sun. They were monsters, many dozens or even hundreds of times more massive than anything we see nearby today. They burned furiously hot, shining brilliantly, but living very short lives, some only a few million years. When they ended, they exploded with unimaginable force, scattering the first heavy elements into space. Those elements, carbon, oxygen, iron, and more, would later become the building blocks of planets, oceans, and life. So in a very real way, the story of endings begins with beginnings. The first stars ended, and in ending they seeded the universe with the material needed for everything that came after. The stars we see now are gentler by comparison, though still staggering in their power. Our Sun, for example, is an ordinary star, a medium-sized ball of glowing plasma that has been burning steadily for 4.6 billion years and will continue for several billion more. Stars like the Sun live long lives because they burn their fuel relatively slowly. Deep inside, in their cores, hydrogen is constantly being fused into helium, and the energy from this process pushes outward, balancing the inward pull of gravity. For as long as that balance holds, a star shines steadily. But fuel is not infinite. Eventually, the hydrogen runs low. When that happens, the delicate balance begins to wobble. Gravity squeezes the core, temperatures rise, and the star starts fusing helium into heavier elements like carbon and oxygen. Depending on the star's size, this process may go through several stages, creating heavier and heavier nuclei. In the most massive stars, the process continues all the way to iron. At that point, fusion no longer provides energy. Gravity wins, the core collapses, and the star dies in a spectacular supernova explosion. Smaller stars like the Sun have quieter deaths. When the fuel runs out, they swell into red giants, shedding their outer layers in beautiful glowing shells called planetary nebulae. What remains at the centre is a dense hot core known as a white dwarf, a star remnant about the size of Earth, but with a mass comparable to the Sun. Over time it cools and dims, fading slowly into darkness. Larger stars, by contrast, end as neutron stars or black holes, objects so extreme that they challenge our understanding of physics. This cycle of birth, life, and death has been repeating for billions of years, and it shapes the fate of galaxies and the universe itself. Every star that forms locks away hydrogen, turns it into heavier elements, and then eventually returns those elements to space through winds, explosions, or collapse. Over countless generations, the composition of the universe changes. Where once there was only hydrogen and helium, now there are all the ingredients for planets and for us. And yet each generation also uses up fuel. The hydrogen that powers stars is not infinite. Every star that burns brings the cosmos one step closer to exhaustion. It's strange to think of stars as timers, but that's what they are. Their lifespans, whether short or long, are measured in predictable ways. A small star, just a fraction of the Sun's mass, might live for trillions of years, far longer than the current age of the universe. A giant star, tens of times larger than the Sun, might burn out in only a few million years. Together, they set the pace of cosmic history. For now, we live in a golden era, when stars are abundant, galaxies glow with light, and night skies are filled with shining patterns. But this abundance is temporary. Already, star formation has slowed compared to its peak billions of years ago. The universe is steadily moving toward a quieter time, when fewer and fewer new stars will be born. Imagine a far distant future when the great star-making factories of galaxies have shut down. Clouds of gas will be used up or blown away, and without fresh fuel, no new stars will ignite. The galaxies will slowly fade as their existing stars age and die. Over unimaginable stretches of time, even the most long-lived red dwarfs, those small, steady stars, will burn through their fuel and wink out. The cosmos, once vibrant with light, will grow darker and colder. And yet stars leave behind more than just darkness. They leave behind black holes, neutron stars, white dwarfs, and all the heavy elements scattered into space. In the very long run, even these remnants change. White dwarfs cool into black dwarfs, invisible cinders. Neutron stars may persist almost unchanged, but black holes dominate the later stages. They gather matter, merge with each other, and in some theories slowly evaporate over unimaginable timescales. Stars may vanish, but their echoes shape the destiny of everything else. From our perspective here and now, stars feel eternal. The sun rises every day, and the night sky has looked essentially the same for all of human history. But cosmic time is far larger than human time. Compared to the lifetime of stars, civilizations are flickers, brief sparks in the dark. Even species are short-lived compared to stellar lifespans. And yet, without stars, we wouldn't be here at all. Their lives and deaths are the reason there is iron in your blood, calcium in your bones, oxygen in your breath. We are, in the most literal sense, made of stardust, the ash of ancient supernovae recycled into life. Thinking about stars as the first timers of the universe gives a sense of rhythm to the cosmos. They mark the passage of cosmic eras, from the wild, short-lived giants of the beginning to the steady suns of the Middle Age, and eventually to the long twilight of faint dwarfs and remnants. Each star's life is a story, and together those stories add up to the history of the universe. And since endings matter for our question, each stellar ending is also a step toward the universe's ending. With every fusion reaction, with every photon of light that escapes into space, the grand reservoir of usable energy shrinks, entropy rises, and the march toward the far future continues. So when we ask how the universe will end, we can't skip over stars. They are both the architects and the fuel of everything we see. Their first appearance marked the universe's transition from darkness to light, and their eventual fading will mark the transition back to darkness again. To talk about cosmic endings is really to talk about the long, slow story of starlight, and the way it carries the universe from one state to another. If stars are the first timers, then galaxies are the vast communities they build together. To picture the universe without galaxies is almost impossible. Each one is a city of stars, sometimes holding hundreds of billions, each star with its own history, its own future, and in some cases its own planets. But galaxies are more than just collections. They have lives of their own, long life cycles that stretch across cosmic time. And just as stars are born, shine, and fade, galaxies too go through stages of birth, growth, transformation, and decline. To understand how the universe may end, we need to look at how these immense structures change over billions of years. The story begins with clouds of gas. After the Big Bang, matter wasn't evenly spread out. Some regions had a little more density than others, and gravity loves unevenness. The slightly denser spots pulled in more gas, which made them denser still, creating a feedback loop. Over millions of years, those regions became the first structures in the universe. Inside them, the first stars ignited, and as groups of stars formed, they naturally clumped into larger gatherings. These gatherings became the earliest galaxies, small and irregular compared to the grand spirals and ellipticals we see today. Galaxies are shaped not only by stars but also by dark matter. Though we can't see dark matter, its gravity holds galaxies together. Without it, stars would fly apart, their orbits too fast to remain bound. Dark matter provides the invisible scaffolding on which galaxies grow, like the frame of a building that supports the visible walls and windows. Around this skeleton, gas condenses, stars form, and structures emerge. So in a sense, galaxies are both luminous and shadowed, their lives guided by something we can't directly detect but can infer from the way they move. Over time, galaxies grow by merging. Picture two great spirals drifting toward each other, pulled by gravity into a slow dance. Their stars weave past one another, their shapes distort and clouds of gas collide, triggering bursts of new star formation. After millions of years of interaction, what remains is a single, larger galaxy, reshaped by the encounter. This process of merging has been happening since the early universe, and it continues today. Even our own Milky Way is on a collision course with the Andromeda Galaxy, due to meet in about 4 billion years. When they merge, they will form a giant elliptical galaxy, with stars flung into new orbits and shapes transformed forever. The life cycle of a galaxy is tied closely to its ability to form stars. Young galaxies are rich in gas, with plenty of raw material for star birth. As time passes, the gas is used up, blown away by stellar winds, or heated by the energy of massive stars and black holes. With less gas available, star formation slows, and the galaxy enters a quieter phase. The light dims gradually, not because existing stars vanish all at once, but because fewer new stars replace the ones that die. In this way, galaxies age. Some remain vibrant with bright blue stars, while others become more subdued, filled with long-lived red stars that glow faintly but steadily. The centre of a galaxy often hides a surprise. Most large galaxies, including our Milky Way, host supermassive black holes at their cores. These black holes can contain millions or even billions of times the mass of the Sun, and when they actively consume matter, they release enormous amounts of energy. Entire galaxies can be lit up by the activity of their central black holes, creating quasars so bright that they outshine everything else around them. This stage, though, is temporary. Once the fuel is gone, the black hole quiets and the galaxy settles into a calmer life. But the influence of these central giants lasts much longer. They shape the flow of gas, regulate star formation, and may even determine how a galaxy evolves over billions of years. As time stretches on, galaxies continue to change. They collide, merge, lose gas, and slowly fade. The Milky Way's eventual merger with Andromeda will be just one of countless such unions across the cosmos. In the far future, galaxies will no longer be separate islands of stars but will clump into even larger structures, held together by gravity. Meanwhile, the expansion of the universe is pulling galaxies away from one another, Over billions of years, distant galaxies will slip beyond our horizon, moving so far away that their light will never reach us. To any future observers, the universe will appear emptier and darker, with only their local cluster of galaxies remaining visible. The life cycle of galaxies, then, is not just about their internal changes, but about their place in the larger universe. They are born from gas, grow by merging, burn brightly with new stars, then gradually quiet down. Their shapes shift from irregular to spiral to elliptical. Their populations change from young hot stars to old red ones. And through it all, they are carried along by the great expansion, scattered farther and farther apart. It's humbling to think about the scales involved. A galaxy's life spans billions of years, far longer than any star within it, far longer than any species or civilization could ever last. And yet, even galaxies are not eternal. In the long view, their star formation stops, their stars die, and their light fades. They leave behind only remnants, black holes, dwarf stars, and slowly cooling embers. This long decline contributes to the broader trend of the universe, the gradual winding down of energy and light. For us, though, galaxies are more than just cosmic structures. They are our home. When you look up and see the faint band of the Milky Way stretching across the sky, you are looking at the structure that has sheltered our Sun and Earth for billions of years. That band of light is the combined glow of hundreds of billions of stars, each one with its own orbit, its own story. And even though the Milky Way is only one among trillions of galaxies, its life cycle is deeply personal to us. Its future shapes our own, because in 4 billion years, when it collides with Andromeda, our night sky will change dramatically. Future humans, if any are still around, will see a sky filled with vast arcs of stars from the approaching galaxy, an unfolding cosmic spectacle unlike anything we've ever witnessed. Eventually the two galaxies will merge, and the Sun will find a new orbit in the transformed structure. To us it may seem violent, but on the scale of stars it's a graceful rearrangement. Collisions rarely cause stars to crash into each other, because the spaces between stars are so vast. Instead, it's the gravitational fields that weave the drama, pulling and reshaping without direct impact. Over time, the merged galaxy will settle into a calmer state, and life within it will go on, if life still exists at all. But the clock will keep ticking. Stars will continue to burn their fuel, galaxies will keep using up their gas, and the universe will march toward a quieter, darker age. In thinking about the life cycle of galaxies, one realizes that their stories mirror the universe itself. A beginning marked by rapid growth and brightness, a middle filled with activity and structure, and an ending where things slow, fade, and cool. Each galaxy is like a verse in the larger song of the cosmos, each one contributing its own line to the story of how everything moves from birth to conclusion. And just as the death of stars contributes to the universe's future, the slow decline of galaxies shapes what comes next. The focus shifts naturally from the individual lives of stars and galaxies to the broader processes that govern them. What is it that drives this long decline? Why does the universe move from order to disorder, from light to darkness? If galaxies tell the story of cosmic communities, then the story of energy is the one that underlies everything they do. Stars shine because of energy released in their cores, galaxies glow because countless stars radiate together, and life itself on Earth is only possible because our star constantly bathes us in a steady stream of light. But there's a catch, one written into the laws of physics so firmly that no amount of wishful thinking can erase it. Energy, once spread out, doesn't spontaneously gather itself back into neat, usable forms. It diffuses, it disperses, it evens out. The universe, for all its brilliance, is slowly dimming. Not in a sudden or catastrophic way, but in a patient, almost gentle drift, like the last embers of a fire settling into ash. This is where entropy enters the story. Entropy is often described as disorder, but it's better thought of as a measure of how spread out energy has become. A hot object placed in a cool room will cool down because the energy leaves the object and flows into the room. Eventually the temperature equalizes and no further change occurs. That's equilibrium. The same principle applies to the cosmos as a whole. Stars burn their fuel, releasing energy into space. That energy radiates outward, absorbed and re-emitted, scattered into wider and wider regions until it blends into the background. Over cosmic timescales, the result is inevitable. The differences in energy that drive change gradually fade away. Right now, the universe is still young and vibrant compared to its eventual future. Galaxies sparkle, stars burn, and cosmic structures remain distinct. But even now, entropy is always increasing. Every star that converts hydrogen into helium, every black hole that swallows matter, every ray of light that escapes into the vastness contributes to the overall trend. The universe is always moving toward a state where energy is evenly distributed and no more useful work can be done. To imagine this slow dimming, think of the night sky. Today, even in the darkest places on Earth, the Milky Way glows faintly as a river of light across the sky. But in the far future, many of those stars will be gone. The gas that forms new stars will have been used up or blown away. Galaxies will fade as their last bright stars die, leaving only red dwarfs glowing faintly, then cooling into darkness. With each passing billion years, the sky grows emptier, the brilliance replaced by faint points scattered thinly across an expanding void. The process is gradual, and that makes it easy to overlook. On human timescales, stars feel eternal. The sun rises, sets, and will do so for billions more years. But scale up to trillions, quadrillions, and beyond, and the picture changes. Entropy ensures that the energy reservoirs that make stars possible will run down. Even the longest-lived stars will eventually exhaust their fuel. When they do, their quiet glow will fade and the cosmos will grow darker still. It's not just stars that dim. Energy also governs the activity of galaxies themselves. When galaxies are young, collisions of gas clouds trigger bursts of star formation. But over time, the gas becomes harder to gather. Supernova explosions, radiation from massive stars, and even the jets of supermassive black holes push gas outward, preventing it from cooling into new stars. As a result, galaxies slow down, entering a kind of middle age where starbirth becomes rarer. The balance tips toward decline. And beyond galaxies lies the vast cosmic web, filaments of matter stretching across space. Even these structures, dramatic as they are, owe their shape to the uneven distribution of matter and energy in the early universe. Over eons, the pull of gravity sculpts the web more finely, but in the end, as dark energy drives expansion faster and faster, even the cosmic web will thin out. Galaxies will drift apart until they're no longer visible to each other, and the large-scale structures of the universe will dissolve into emptiness. Energy, spread too thin, will no longer create new forms. Entropy doesn't destroy energy. That's important to remember. The total amount of energy in the universe remains constant. What changes is its usefulness. Energy in a concentrated form can do work. It can move things, power stars, fuel life. Energy that's spread evenly across space. Like lukewarm tea left too long, can no longer drive change. The universe may continue to contain energy, but in the end it will be too evenly distributed to matter. That's why scientists sometimes describe the ultimate fate as a heat death. Not because it ends in fire, but because it ends in uniform warmth, with no pockets of difference left to keep the story going. Right now, we live in an age of remarkable imbalance. Stars shine because their cores are hot compared to the cold vacuum of space. Black holes consume matter because gravity is stronger than the outward push of particles. Life exists because energy flows from hot sources like the sun to cooler places like Earth. Everything interesting happens in these imbalances, in the differences, but entropy tells us that those differences are temporary. The universe is evening itself out slowly, steadily, inexorably. It might sound bleak, but it doesn't have to be. In fact, the slow dimming gives us a kind of perspective. The very fact that energy still flows, that entropy is still increasing, is why we exist in the first place. Our lives are possible because we live during the long middle chapters of the cosmos, when stars still burn and galaxies still glow. The quiet inevitability of the dimming makes this moment feel all the more precious. Looking far into the future, the dimming unfolds in stages. First, star formation stops. Then, existing stars burn out. Over trillions of years, only faint dwarfs remain, glowing red against the darkness. Eventually, even they fade into black dwarfs, invisible in the night. Galaxies will become graveyards, filled with remnants, but no light. Black holes will linger, swallowing what little matter remains, before slowly evaporating through Hawking radiation. And in the farthest reaches of time, even particles themselves may decay, leaving a thin soup of radiation stretched across space. Each stage marks a step toward equilibrium, toward the final stillness. It's difficult to truly grasp these timescales. Billions of years already stretch the imagination, but the endgame of the universe requires numbers so vast that they almost cease to mean anything. 10 to the power of 100 years is a timescale often used to describe the long fade, a number so large it dwarfs every human comparison. To us, it may as well be forever, and perhaps that's the point. The universe's dimming is not something we need to fear or even expect to witness. It's part of a story that unfolds far beyond us, but still includes us, if only for a brief shining instant. This slow dimming connects directly to the broader possibilities we considered earlier. If the universe continues expanding under the influence of dark energy, the dimming becomes the dominant path, leading to heat death. If expansion changes, other outcomes are possible, but in every case, entropy plays its role. Whether the cosmos collapses, rips apart, or simply fades, the flow of energy from order to disorder never reverses. It's the drumbeat beneath all the other theories, the one constant in a universe filled with change, and while scientists explore the details, the philosophical questions linger too. What does it mean for everything to fade? Is an end of light also an end of meaning? Or does the story of the universe continue in ways we can't yet imagine, with quantum fluctuations or cycles that reset the stage? Those questions remain open, but the physics we do know already tells a compelling tale. It tells us that energy is not endless, that the light we see is temporary, and that the universe, magnificent as it is, will one day grow still. Entropy is one of those words that sounds technical and abstract, the kind of term you might encounter in a classroom or buried deep in a physics textbook. Yet behind the word lies one of the most important ideas for understanding the universe. It is the quiet principle that explains why hot tea cools, why stars burn out, why galaxies eventually fade, and why the universe, in the longest view, is headed towards stillness. To explore the fate of everything, we have to sit with entropy for a while, not as a cold equation, but as a companion that has been guiding the universe since the very beginning. At its heart, entropy is about the difference between order and disorder, or more precisely, the number of possible arrangements that a system can take. A neat deck of cards has one arrangement. Shuffle it, and suddenly there are countless ways those cards could be ordered. The messy deck represents more possibilities, more disorder, and therefore more entropy. The universe works in much the same way. When energy and matter are concentrated, there are fewer possible arrangements. As they spread out, the number of arrangements skyrockets and entropy increases. The second law of thermodynamics says that in a closed system, entropy always increases. The universe is the ultimate closed system, so its entropy is always rising. That doesn't mean that everything becomes messy all the time. Local pockets of order can and do emerge. Stars form from clouds of gas. Planets take shape. Life arises and organizes itself into intricate patterns. But these local decreases in entropy always come at the expense of a greater increase elsewhere. A star creates order in its core, but only by radiating energy outward into space. Life maintains its structure by constantly taking in energy from the environment. Entropy never stops rising overall. This ever-growing disorder may sound bleak, but it's the very reason why things happen at all. Without entropy, energy would never flow, heat would never move from hot to cold, stars would never shine, and life would never evolve. Entropy is not just about endings, it is also about motion, change, and the arrow of time itself. The reason we feel time moving forward, the reason memories exist of the past but not the future, is deeply connected to entropy's relentless increase. The universe began in a state of low entropy, smooth and uniform, and it has been drifting toward higher entropy ever since. That drift is what gives time its direction. Think of the early universe just after the Big Bang. Everything was hot, dense, and astonishingly uniform. At first glance, uniformity seems like disorder, but in physics it was actually a state of low entropy, because there were relatively few possible arrangements for matter and energy in such a smooth condition. Over time, small fluctuations grew under the pull of gravity, creating clumps that became galaxies, stars, and planets. In this sense, the growth of structure was also the growth of entropy. The universe was moving toward more possible states, more variety, more disorder overall, even as it created local order along the way. When we look at galaxies today, glowing with billions of stars, we are looking at entropy in motion. Each star is a nuclear furnace converting matter into energy, radiating heat into space. Every photon of light streaming across the void increases the universe's entropy. Over billions of years, this process accumulates, spreading energy thinner and thinner. The stars that light the night sky are therefore both beacons of order and engines of disorder, accelerating the long drift. One way to feel entropy's effect is to notice how energy differences power everything. When there's a difference in temperature, heat flows. When there's a difference in pressure, air moves. When there's a difference in charge, electricity flows. All of these processes reduce differences and increase entropy. Eventually differences run out. The tea cools to room temperature. The batteries run down. The air pressure equalizes. Without differences, there is no flow, no change, no life. The universe is moving steadily in that direction, from a place of great contrast to a place of sameness. That sameness is not something we will see soon. The universe is vast and entropy's drift is slow on human timescales. Stars will continue to shine for trillions of years. Galaxies will continue to evolve and life in some form may continue to arise wherever energy still flows. But the overall trend is unavoidable. Each burst of light, each collision of galaxies, each supernova explosion adds to the ledger of entropy, carrying the cosmos closer to equilibrium. The drift toward disorder also explains why perpetual motion machines remain impossible. People have dreamed of creating devices that run forever without input, producing endless energy from nothing. But entropy rules this out. Energy always spreads out. Some of it always becomes unavailable for work. Even the most efficient machine would eventually lose energy to heat, friction, or radiation. The dream of endless motion runs aground on the reality of entropy's law. The same principle applies to the universe as a whole. No process can continue forever without change, because energy differences cannot be maintained indefinitely. It's striking to realize how deeply entropy shapes our daily lives. When you cook food, when you breathe, when you charge your phone, you're witnessing energy flowing from high concentration to low, creating entropy. Even the act of thinking, as your brain processes information, produces heat and adds to the universe's disorder. Every moment, without exception, contributes to the long drift. It may feel invisible, but it is constant. In the cosmic future, entropy will continue to guide the story. As galaxies stop forming stars, as black holes swallow matter, as radiation fills the emptiness, the universe will grow more uniform. Black holes themselves, once thought to be eternal, leak energy slowly through Hawking radiation. Over unimaginable timescales, they too will evaporate, adding their mass to the pool of dispersed energy. What remains will be a thin haze of particles and photons spread across an ever-expanding space. That state represents maximum entropy, the endpoint where nothing more can happen. Some scientists and philosophers find this endpoint unsettling. A universe without change seems lifeless, static, and final. Others see it as simply another stage, the natural consequence of the laws that gave us stars, galaxies, and life in the first place. After all, entropy has always been there, shaping events from the very start. To imagine a universe without entropy is to imagine a universe without time, without flow, without the very fabric of experience. In that sense, the drift toward disorder is not just inevitable, it's fundamental to existence itself. It's also worth noting that entropy, while relentless, is not the whole story. Quantum mechanics suggests that even in a state of maximum entropy, fluctuations may still occur. Tiny random differences could emerge, creating pockets of lower entropy again, perhaps even new universes. This idea pushes us beyond the borders of current science into speculation, but it shows that even at the edge of endings, entropy leaves room for mystery. For now, though, the picture is clear enough. Entropy is the tide carrying the universe forward. It explains why stars shine and why they will one day fade. It explains why time feels like it moves in one direction. It explains why the ultimate fate of the cosmos, whatever form it takes, will be shaped by the dispersal of energy into balance. The long drift toward disorder is not just a detail. It is the foundation of the universe's story. When people first hear the phrase heat death of the universe, they often imagine something fiery, dramatic, maybe even violent, as though the cosmos will end in a sudden blaze. The truth, though, is much quieter, more subtle, and in some ways more unsettling. Heat death does not come with an explosion. It arrives slowly, silently, as the energy that once powered stars, galaxies, and life itself spreads so thin that nothing meaningful can happen anymore. To understand it, you can think of a fire burning in a hearth. At first it blazes bright, warming the room. Slowly, though, the logs burn down, the flames shrink, and eventually only faint embers remain. After enough time, even those embers cool, leaving only ashes and cold stone. The heat death of the universe is like that, only stretched across unimaginable timescales. The name itself is a bit misleading. It doesn't mean the universe will get hotter, quite the opposite. It means that temperature differences will vanish. Right now, the universe is full of contrasts. Stars are hot, space is cold, and the energy flows between them drive everything we see. The sun shines because its core is far hotter than its surroundings. Planets orbit because of the energy stored in gravity. Life thrives because of the constant stream of sunlight striking a cooler Earth. But in the long run, these differences disappear. Energy spreads evenly, temperatures equalize, and the contrasts fade. When everything's the same temperature everywhere, there is no more flow, no more change, no more story. That is heat death. The road to this silent fate is long, so long that even words like billions and trillions begin to lose meaning. For a while, the universe will look much as it does now. Stars will continue to form, though at a slower pace. Galaxies will continue to shine, though a little dimmer with each passing billion years. The cosmos is already past its most productive era of star formation, and new stars are born less often than they once were. Still, the night sky will remain beautiful for a very long time. Eventually, though, the gas that fuels new stars will run out. Supernova, stellar winds, and black holes will expel or consume much of the remaining material. Star formation will dwindle, and then stop altogether. The stars already burning will continue to shine, but as the eons stretch on, one by one they will exhaust their fuel. First the massive stars, then the medium ones like the Sun, and finally the long-lived dwarfs that persist for trillions of years. The night sky will gradually shift from one filled with brilliant blue and yellow stars to one lit only by faint red embers. And then, even those embers will fade into darkness. What remains after the stars die are their remnants. White dwarfs, neutron stars and black holes will populate the darkened galaxies. White dwarfs will cool and dim, eventually becoming black dwarfs, cold objects invisible in the dark. Neutron stars will persist, dense and heavy, but largely quiet. Black holes will dominate, swallowing what little matter remains nearby. Over time, even these remnants will interact, colliding, merging, or drifting apart. But the universe's brilliance will be gone, replaced by a faint scattering of dark remnants across vast emptiness. The final act in this long decline involves the black holes themselves. For many years they were thought to be eternal, perfect prisons from which nothing could escape. But in the 1970s, Stephen Hawking showed that even black holes can lose energy. Through a quantum effect near their event horizons, they emit tiny amounts of radiation. Over incomprehensibly long spans of time, this process, Hawking radiation, will cause black holes to evaporate. The largest ones will take far longer than the age of the universe so far, but eventually even they will vanish, releasing their mass as faint radiation into the void. When the last black holes have evaporated, the universe enters its final stage. What remains is a thin soup of particles and photons, spread across an expanding cosmos. Temperatures everywhere are nearly the same, just a fraction above absolute zero. With no energy differences, nothing new can happen. No stars, no galaxies, no life, not even the faint glow of dying black holes. Just uniform, endless stillness. That is the heat death of the universe. It's a strange fate to imagine, because it lacks the drama we often expect from endings. There is no cataclysm, no explosion, no sudden collapse. Instead, it's a slow fading, a gentle winding down. If you could somehow stand in that future, there would be no grand finale, only the quiet absence of change. From the perspective of physics, that silence is final. Without differences in energy, there are no processes left to unfold. The arrow of time has reached its destination, and yet, in thinking about this possibility, it's worth remembering that we live in the golden age of the cosmos. Right now, stars shine, galaxies glow, and the night sky is filled with light. We are here during the middle chapters, when entropy has not yet reached its maximum, when contrasts still drive the richness of the universe. The fact that we can even ask about heat death is a reminder of how unusual this moment is. We exist during the time when the universe is still alive with motion, before the long silence to come. For some, the thought of heat death feels bleak, as though the universe's story ends in emptiness and futility. But there's another way to see it. The same laws of thermodynamics that lead to this quiet ending are the ones that gave us stars, planets, and life. Without entropy, energy would not flow and we would not exist. Heat death is not separate from the universe's beauty. It is the farthest echo of the same processes that allowed us to be here at all. There are also hints of mystery even in this seemingly final picture. Quantum mechanics, with its strange fluctuations, suggests that even in a uniform, high-entropy universe, random variations could occur. Tiny pockets of order might appear, perhaps even regions that resemble new universes. This idea remains speculative, but it shows that even the silence of heat death may not be absolute. Physics leaves room for possibilities we don't yet fully grasp. Still, the main idea is clear. If expansion continues, if entropy rises without reversal, then the universe is heading toward a quiet twilight where nothing more can happen. The stars will fade, the galaxies will vanish, the black holes will evaporate, and the cosmos will settle into equilibrium. That is one possible ending, perhaps the most widely accepted among scientists today. Heat death paints a picture of endless expansion and fading light, but there is another vision of the universe's fate that feels almost like its mirror image. Instead of stretching into silence, the cosmos could one day reverse direction, folding back in on itself until everything that now exists is compressed into an unimaginably dense state. This possibility is called the Big Crunch, and it offers a very different ending to the universe's story. Rather than a slow dimming, it is a dramatic collapse, a reversal of expansion, and perhaps even the prelude to something new. To imagine the Big Crunch, it helps to return to the discovery that the universe is expanding. Galaxies are not fixed in place. They are receding from each other as space itself stretches. This expansion was first noticed in the early 20th century, when astronomers observed that light from distant galaxies was shifted toward the red end of the spectrum, evidence that those galaxies were moving away. Extrapolating backward, it became clear that the universe must once have been much smaller, denser, and hotter. That realization gave rise to the idea of the Big Bang. If the universe began with expansion, the next natural question was whether that expansion would go on forever, or eventually slow and reverse. Gravity is always pulling matter together. Every galaxy, every star, every particle contributes to the overall gravitational pull of the cosmos. For a long time, scientists wondered whether there was enough matter for gravity to halt the expansion. If the pull was strong enough, space might stop stretching and begin to contract. Galaxies would draw closer, clusters would merge, and over time the entire universe would shrink back into a dense state. That would be the Big Crunch, the opposite of the Big Bang. In this vision, the universe's life has a symmetry. It begins with an explosion of expansion, grows and evolves for billions of years, and then collapses in a fiery finale. Stars, galaxies, and all structures would be crushed as the cosmos contracts. Temperatures and densities would soar. Physics as we know it might break down under the extreme conditions. The end would look a lot like the beginning, a universe returning to a state where all distances vanish, and all matter is compressed into a singular point. This picture is compelling because it feels balanced. A beginning and an end, an expansion followed by contraction. It resonates with the idea of cycles, something that appears throughout nature. Day and night, seasons, birth and death. All of these follow patterns that repeat. The Big Crunch offers a cosmic version of that cycle, where the universe itself follows a rhythm of expansion and collapse. Some scientists have even suggested that the Big Crunch might not be the end at all, but the trigger for a new beginning. If the universe collapses into a singular state, perhaps it could rebound, exploding outward once more in a new Big Bang. In this way, the cosmos might be eternal, not in the sense of remaining unchanged, but in endlessly repeating cycles of birth, growth, and collapse. This idea is sometimes called the oscillating universe model, and while it remains speculative, it has a certain elegance. It suggests that endings are never final, but part of a larger loop. However, the fate of the universe depends on more than elegance. It depends on the actual density of matter and the behavior of dark energy. For the Big Crunch to happen, the pull of gravity must eventually overcome the push of expansion. For decades, astronomers measured the amount of matter in the universe, trying to determine whether there was enough to slow expansion. At first, it was not clear. Observations showed that galaxies contain far more mass than we can see, leading to the discovery of dark matter. Perhaps this invisible substance provided the necessary pull. Then, in the late 1990s, observations of distant supernovae revealed something unexpected. The expansion of the universe was not slowing down at all. It was accelerating. This acceleration implied the presence of dark energy, a mysterious force pushing space apart. With dark energy dominating the cosmos, the Big Crunch seemed less likely. Expansion was not just continuing, it was speeding up. Instead of reversing, the universe appeared destined to expand forever. Still, The Big Crunch has not been ruled out completely. Dark energy remains one of the greatest mysteries in science. We know it exists because of its effects on expansion, but we do not know its true nature. If dark energy is not constant, if it changes over time, then the fate of the universe could be different. It is possible that what looks like acceleration today could slow in the far future, allowing gravity to regain control. If that happened, expansion could halt and contraction could begin. The cosmos would then march slowly toward its inward collapse. The timeline for such a collapse would be vast. First, galaxies would stop drifting apart and begin to fall toward one another. Large-scale structures like galaxy clusters would merge, forming ever denser clumps. The night sky would grow brighter, not darker, as galaxies crowded closer together. Over billions of years, the density would rise, temperatures would increase, and eventually stars and planets would be torn apart. Black holes would merge, and their combined gravity would intensify the collapse. In the final stages, all of space would curve inward, all matter compressed into a state of infinite density. The Big Crunch is difficult to picture because it requires imagining everything collapsing everywhere at once. Unlike a black hole, where matter falls inward toward a single point in space, the Big Crunch is the collapse of space itself. There is no outside to fall into, no external vantage point from which to watch. The stage on which everything exists is shrinking, folding, compressing. To an observer within it, distances shrink, horizons close in, and the universe itself grows hotter and denser. Whether this collapse would be the absolute end or the beginning of something new remains unknown. If physics allows for a rebound, then the Big Crunch could be followed by a new Big Bang. The universe might be cyclic, endlessly repeating, with each cycle giving rise to new structures, new stars, new possibilities. In such a model, our own universe would be just one act in an infinite play. But if no rebound occurs, then the crunch would be final, the last moment of existence with no continuation beyond it. The appeal of the Big Crunch lies not only in its symmetry, but also in the way it connects us to the universe's history. Just as the Big Bang marked a moment of creation, the Big Crunch would mark a moment of closure. It frames the cosmos as a story with a beginning and an end, not an endless drift into silence, but a dramatic conclusion that mirrors its birth. That story feels satisfying, even if reality may not match it. Still, the evidence we have today points away from this possibility. Dark energy's accelerating push seems to make a crunch unlikely. Yet science is always provisional, always open to new discoveries. If dark energy behaves differently than we think, if its strength changes over time, then the door to collapse could reopen. Until we understand dark energy fully, the Big Crunch remains one of several possibilities, a reminder that the universe may still surprise us. And even if the Big Crunch never happens, thinking about it sharpens our perspective on other scenarios. It reminds us that the cosmos is not static, that expansion and contraction are both possible outcomes of the same basic laws. It highlights the delicate balance between gravity pulling inward and dark energy pushing outward. And it raises profound questions about cycles, about whether time itself might loop, and about whether endings might also be beginnings in disguise. The Big Crunch imagines gravity winning the long tug of war, pulling everything back together. Heat Death imagines expansion winning slowly, leaving only silence. But there is another possibility, one that feels more violent, more dramatic, almost apocalyptic in its imagery. Instead of fading away or collapsing inward, the universe could end by tearing itself apart. Every galaxy, every star, every planet, and even every atom pulled to pieces by expansion itself. This scenario is called the Big Rip, and it represents one of the most extreme fates the cosmos might face. To understand the Big Rip, we need to return again to dark energy. This mysterious force is the reason the universe's expansion is accelerating. Galaxies aren't just drifting apart, they're doing so faster and faster. The discovery of this acceleration in the late 1990s shocked scientists. It suggested that something in the fabric of space itself was driving galaxies apart. Dark energy is still poorly understood, but the simplest explanation is that it is a constant property of space. Each region of space has the same amount of dark energy, and as space expands, more space means more dark energy. That would explain why expansion accelerates. But what if dark energy is not constant? What if it grows stronger over time? If its repulsive effect increases, then expansion won't just accelerate. It will run away, becoming faster and faster until it overwhelms every force in nature. This runaway expansion is the essence of the Big Rip. The same force that gently spreads galaxies apart today could, in the distant future, pull apart stars, planets, molecules, and even the fabric of matter itself. The timeline of a Big Rip universe is startling to imagine. At first, the effects are subtle. Galaxies drift away as they do now, just a bit faster, but as time passes, the acceleration grows. Galaxies no longer just recede from one another, they begin to dissolve. The gravity that holds stars together within galaxies becomes too weak to resist the expansion of space. Galaxies unravel, scattering their stars into isolation. Then the stars themselves become vulnerable. Expansion accelerates to the point where it overcomes the gravity binding stars together. Planets orbiting those stars are stripped away. Solar systems disintegrate, leaving planets adrift in widening voids. Eventually, even planets themselves can no longer hold together. The forces binding their matter are pried apart by expansion. Worlds shatter into fragments, then into dust, then into particles. And the process does not stop there. As the rip approaches its climax, the very atoms that make up matter can no longer resist. The forces binding electrons to nuclei are overcome. Atoms tear apart, and matter itself dissolves into fundamental particles, which are then scattered into nothingness by the runaway expansion of space. Finally, even the fabric of space-time is torn, ripped into a state where the very concept of distance loses meaning. The Big Rip is so dramatic because it is not simply the fading of light or the collapse of matter. It is the destruction of the underlying fabric that makes matter possible at all. Unlike heat death, which drifts toward equilibrium slowly, or the Big Crunch, which ends in compression, the Big Rip ends in disintegration, in the ultimate unravelling of everything. When scientists talk about this scenario, they often estimate how long it would take if dark energy were to behave in this runaway way. Depending on the details, the timeline could range from tens of billions of years to perhaps only a few billion beyond today. The exact number depends on the strength of dark energy and how it evolves. Right now, observations suggest that dark energy is constant, which makes a Big Rip unlikely. But because we don't fully understand its nature, the possibility remains open. It's sobering to think that the same gentle expansion that allows the universe to evolve could also contain the seeds of such a catastrophic ending. Right now, dark energy is so weak on human scales that we barely notice it. Galaxies drift apart, but stars within galaxies remain bound. Gravity still rules locally. But if dark energy grows stronger, its dominance spreads inward, overwhelming smaller and smaller structures until nothing is left. The Big Rip highlights just how little we know about dark energy. We can measure its effects on the large scale, but its true nature remains hidden. Is it a constant property of space? Is it something that changes over time? Could it even be a sign of new physics we have not yet discovered? The answers to these questions determine not just the fate of galaxies, but the fate of everything. From a human perspective, the Big Rip is hard to imagine because it is so unlike our daily experience. We are used to things falling apart through decay, through wear and tear, through entropy's quiet work. But we're not used to imagining space itself as an agent of destruction. Expansion feels like nothing at all. It is not a force we can touch or feel. Yet in this scenario, it becomes the most powerful force of all. strong enough to unmake everything. At the same time, the Big Rip carries with it an odd kind of symmetry. Just as the universe began with a rapid expansion in the Big Bang, it could end with an even faster expansion that tears it apart. In both cases, expansion is the key. First, it created the space in which galaxies could form, and then, in the end, it could destroy those galaxies entirely. The story of the universe would then be bookended by expansion. One creative, one destructive. For those who think about these endings, the Big Rip often feels like the most unsettling. Heat death at least leaves a quiet, if lifeless, universe. The Big Crunch suggests a return to beginnings. But the Big Rip offers no stillness, no cycle, only destruction. The structures that exist today would not simply fade, but would cease to exist entirely. Even the particles that make up matter would be torn apart. It is a vision of an ending when nothing survives. And yet, as extreme as it is, the Big Rip remains a possibility precisely because of how little we know about dark energy. It reminds us that the universe is not fully mapped, that the most fundamental force shaping its destiny is still a mystery. Every measurement of cosmic expansion is a clue, every observation of distant galaxies a piece of the puzzle. Until we know more, the Big Rip must remain on the table, a scenario both frightening and fascinating. Among all the objects in the cosmos, black holes stand out as the strangest and most enduring. Stars are born, shine, and eventually fade. Galaxies form, evolve, and slowly decline. But black holes seem to sit outside that familiar rhythm, as if they are actors who step onto the stage only in the later acts, commanding attention with their gravity and refusing to leave even after everything else has gone. If the universe is a play unfolding across unimaginable spans of time, then black holes may be the last performers, lingering in the spotlight long after the galaxies have dimmed and the stars have burned away. To see why they hold such a lasting role, it helps to think about what a black hole actually is. Despite their name, they are not holes in the sense of gaps or voids. They are regions of space where gravity has become so intense that nothing, not even light, can escape. A black hole forms when a massive star collapses under its own weight at the end of its life. The core is squeezed so tightly that it forms a singularity, a point of infinite density surrounded by an event horizon, the boundary beyond which escape is impossible. From the outside, black holes appear dark and silent, but their influence is anything but passive. The gravity shapes everything around them, bending space, distorting time, and pulling in matter that strays too close. There are different kinds of black holes. Some are formed from stars several times the mass of the Sun, collapsing into objects only a few kilometers wide. Others are far larger, millions or billions of times the mass of the Sun, lurking at the centers of galaxies. These supermassive black holes are mysteries in their own right. How did they grow so large? Were they born in the earliest days of the universe, or did they slowly feed on matter and merge with other black holes to reach their enormous sizes? Whatever their origins, they now sit at the heart of galaxies, shaping their evolution in subtle but profound ways. In the current era of the universe, black holes are already playing a significant role. They power some of the brightest phenomena we know, such as quasars, where matter falling into a supermassive black hole releases energy on a scale that can outshine an entire galaxy. They drive jets of particles that extend across millions of light years, altering the flow of gas and influencing where new stars can form. They act as anchors for galaxies, helping to stabilize structures across vast scales. Yet all of this is just the beginning of their story. As stars fade and galaxies quiet down, black holes will remain. Unlike stars, they do not burn fuel. They are not dependent on fusion or delicate balances between pressure and gravity. They are stable, persistent, and enduring. As the universe ages, ordinary matter will dwindle, but black holes will continue to exist, swallowing what they can and merging with one another when their paths cross. Over trillions upon trillions of years, the universe will grow emptier, but black holes will still sit in the darkness, massive and silent. Eventually, black holes will become the dominant structures in the cosmos. When the last stars have burned out, when galaxies no longer shine, black holes will still be there, the final remnants of a more vibrant age. They will drift through the dark, consuming stray matter and radiating nothing visible. The universe will be populated by them, sparse but enduring, like a theatre where only a few actors remain on stage after the play has long since ended. But even black holes are not eternal. In the 1970s, Stephen Hawking discovered that black holes are not perfectly black. Through quantum effects near the event horizon, they emit tiny amounts of radiation. This process, now called Hawking radiation, causes black holes to lose mass, ever so slowly. For small black holes, the effect is stronger, and they evaporate more quickly. For massive black holes, the process is incredibly slow, taking far longer than the current age of the universe. But given enough time, all black holes will eventually evaporate, disappearing in a faint burst of radiation. The timescales involved are almost beyond comprehension. A black hole with the mass of the Sun would take around 1067 years to evaporate. A supermassive black hole with billions of solar masses could take up to 1000 years or more. These numbers dwarf the current age of the universe, which is only about 14 billion years. In other words, black holes will outlast everything else by a staggering margin. Long after galaxies have disappeared, long after stars are gone, long after matter itself has decayed, black holes will remain, slowly evaporating in the dark. As they radiate away, the universe will enter what some scientists call the black hole era. It is a time when the cosmos is dominated not by stars or galaxies, but by these silent giants. Occasionally black holes may collide, sending ripples of gravitational waves across the void. Occasionally, they may consume stray matter or merge with smaller remnants, but for the most part they will sit in quiet persistence, the last great structures of a fading universe. When the final stages of evaporation arrive, the process speeds up. A black hole that has been losing mass for trillions of years will suddenly brighten in its last moments, releasing a burst of energy as it vanishes. Each black hole ends in a flicker of radiation, a faint echo of the vastness it once represented. Over time, one by one, they will all evaporate. The largest, the supermassive ones, will be the last to go, disappearing after unimaginable stretches of time. When the last of them vanishes, the black hole era will end, and the universe will move into its final phase, filled only with a thin, uniform bath of radiation. In this way, black holes are the final actors in the cosmic play. They outlast stars, galaxies, and even ordinary matter. They remain when everything else has gone quiet. And then, finally, they bow out too, leaving the stage empty. The story of the universe continues without them, but their presence marks the end of an era, the closing of one of the longest acts in cosmic history. It is striking to realize how central black holes are to the fate of everything. For a long time, they were thought of as exotic curiosities, strange objects on the fringes of science. Now we know they are not rare but abundant, shaping galaxies and driving cosmic evolution. And in the far future, they will be the last great structures left. Their story is not just one of destruction, but of endurance, persistence, and eventual transformation. Thinking about black holes as the final actors can feel eerie. They're so unlike anything else we know, so extreme in their nature, so detached from the familiar cycles of birth and death. And yet they are part of the same universe that gave us stars, planets, and life. Their gravity is the same force that keeps you on Earth, only amplified to unimaginable extremes. Their story is our story too, extended across scales so vast that it feels almost infinite. And as the black hole era unfolds, another question arises. What happens when even the black holes are gone? What does the universe look like when the final actors have left the stage, and only the empty theatre remains? When most people first hear the phrase black hole evaporation, It sounds like a contradiction. Black holes are supposed to be the ultimate prisons of the universe, objects so powerful in their gravity that nothing can escape. Not light, not matter, not even information. The very name suggests permanence, a place from which there is no return. And yet, physics tells us that even black holes do not last forever. Over the longest time scales imaginable, they slowly leak energy, fading away into the emptiness of space. This slow release is called Hawking radiation, and it reshaped how we think about the universe's future. The story begins with quantum mechanics, the branch of physics that deals with the smallest scales. In quantum theory, empty space is never truly empty. Even the vacuum is alive with activity, with pairs of particles flickering in and out of existence for the briefest moments. Normally, these virtual particles appear together and then annihilate one another almost instantly, returning their borrowed energy to the vacuum. But near the event horizon of a black hole, the rules change. If such a pair appears right at the edge, one particle might fall into the black hole while the other escapes. To an outside observer, it looks as though the black hole has emitted a particle. Stephen Hawking realised that this process means black holes are not completely black. They radiate very faintly due to quantum effects at their horizons. Over time, this radiation carries away energy, and because mass and energy are equivalent, the black hole loses mass. Slowly, patiently, it shrinks. This process is unimaginably slow for large black holes. A black hole the mass of the Sun would take around 1067 years to evaporate, a number so vast it makes even the current age of the universe look brief. For supermassive black holes, with millions or billions of solar masses, the timescales grow even longer, reaching up to 100 years or more. But however long it takes, the outcome is the same. Black holes do not last forever. At first, the radiation is almost undetectable. For a black hole the mass of a star, the temperature of this radiation is far colder than the background of the universe itself. It is drowned out by the faint glow of the cosmic microwave background, the leftover radiation from the Big Bang. Only when the universe has expanded and cooled enough, trillions upon trillions of years into the future, will Hawking radiation begin to dominate. By then, most stars will be gone, galaxies will be dark, and black holes will be the main remaining structures. As evaporation continues, the process accelerates. The smaller a black hole becomes, the hotter it gets and the faster it radiates. In its final stages, after eons of slow shrinkage, the black hole will brighten dramatically, releasing a burst of radiation before disappearing completely. The larger the black hole, the longer this final act takes to arrive. But in every case, the story ends the same way. The mighty gravitational trap, once thought eternal, vanishes in a final flicker. The implications of this discovery are profound. Before Hawking's insight, black holes were seen as permanent features of the cosmos. They might swallow matter and merge with each other, but they would never truly go away. With Hawking radiation, the picture changed. Suddenly, even the darkest, most enduring objects in the universe had lifespans. The black hole era, once imagined as endless, now has an endpoint. One by one, over incomprehensible spans of time, black holes will evaporate until none remain. This realization reshapes our view of the universe's ultimate fate. If heat death is the long slide toward equilibrium, then Hawking radiation is one of the last steps in that process. By converting black holes into radiation, it ensures that even these final actors leave the stage. The universe is stripped of its last structures, reduced to a thin bath of particles and photons spread across ever-expanding space. In that future, nothing remains to change or evolve. The story quiets completely. But Hawking radiation raises deep questions as well. Questions that reach into the foundations of physics. One of the most debated is the information paradox. When matter falls into a black hole, what happens to the information about its state? According to quantum mechanics, information cannot be destroyed, But if a black hole evaporates completely, where does that information go? Is it encoded in the radiation somehow? Does it escape in subtle ways? Or does physics need to be rewritten to resolve the paradox? These questions remain open, fueling debates that stretch across cosmology, quantum mechanics, and the search for a theory of everything. For our journey through the universe's fate, though, the key idea is simpler. Black holes, for all their endurance, are not immune to time. They will persist far longer than stars or galaxies, but even they cannot escape the long pull of entropy. Their evaporation ensures that the universe has no eternal structures. Nothing lasts forever. To picture this far future is almost impossible, yet strangely calming. Imagine a universe so old that stars are only memories, galaxies invisible, and the night sky dark. Only black holes remain, scattered across a vast emptiness. For trillions upon trillions of years they sit in silence, occasionally colliding, occasionally feeding, but mostly enduring. Slowly, imperceptibly, they radiate, losing mass so slowly that no single moment marks a change. And then finally, after ages that make even eternity feel small, each one ends in a flicker. The giants vanish, leaving behind only faint radiation that spreads thinly across infinite space. In that moment, the universe transitions from the black hole era to what some call the dark era. No more stars, no more galaxies, no more black holes, only particles drifting in silence, a cosmos emptied of structure. It is as close as physics comes to a true ending, though even here there may be mysteries left. Some theories suggest that quantum fluctuations in such an empty universe could spark new beginnings, perhaps even new universes. Whether that is true or not, the evaporation of black holes sets the stage. It is strange in a way to realize that something so powerful, so seemingly eternal, ends with a whisper rather than a roar. Black holes, which can devour stars and bend light itself, fade away not through violence but through patience. They evaporate not in seconds or minutes but in spans of time so vast they defy imagination. And yet, their fate is sealed, written into the laws of physics themselves. Thinking about Hawking radiation also gives us a sense of scale for our own lives. We measure time in hours, days, years, perhaps decades. Black holes measure their existence in powers of 10 that stretch beyond comprehension. To compare a human lifetime to the evaporation of a black hole is to compare the flicker of a candle to the burning of a star. And yet, both are part of the same story, governed by the same laws. The physics that dictates the fading of black holes is the same physics that shapes your every breath. The evaporation of black holes is not something we will ever witness directly. It unfolds too slowly, too far in the future for any civilization to see, and yet, knowing about it changes the way we see the cosmos. It reminds us that permanence is an illusion, that even the most unyielding structures are subject to time. It humbles us with the vastness of cosmic scales, but it also connects us to them. We are made of the same matter, governed by the same laws, subject to the same entropy. After the stars have gone out, after galaxies have faded into silence, the universe enters a new age. It is a time without the brilliance of starlight, without the familiar cycles of birth and death that once defined cosmic history. Instead, what remains are the remnants, the cooled and darkened corpses of stars that once burned. This is sometimes called the era of degenerate matter, and it represents one of the longest and strangest chapters in the universe's story. To understand what this era looks like, we need to revisit what happens when stars die. Large stars end in supernova explosions, collapsing into neutron stars or black holes. Smaller stars, like our Sun, end more quietly. After swelling into a red giant and shedding its outer layers, what remains is a dense core called a white dwarf. White dwarfs are extraordinary objects. They are roughly the size of Earth but contain a mass comparable to the Sun. Their matter is packed so tightly that atoms are stripped apart, leaving a sea of nuclei and electrons squeezed together. The pressure that holds them up is called electron degeneracy pressure, a quantum effect that arises from the strange rules of the microscopic world. In the era of degenerate matter, the universe will be filled with objects like these: white dwarfs, neutron stars and brown dwarfs, the failed stars that never ignited fusion, will drift through the darkness. There will be no new stars forming, no fresh bursts of light. The fuel is gone. The galaxies will be graveyards of stellar remnants, populated not by shining suns but by silent compact husks. At first, white dwarfs still glow faintly. They retain heat from the fusion reactions that once burned in their cores, and they radiate that heat away over billions of years. But without new energy being generated, they cool steadily. Over unimaginable spans of time, they fade to black dwarfs, cold and dark objects that emit no light at all. These black dwarfs are the ultimate stellar corpses, invisible in the darkness, detectable only by their gravity. Neutron stars, too, will persist. Born from the collapse of massive stars, they're even denser than white dwarfs, packing the mass of the Sun into a sphere only a few kilometers across. Their matter is held up not by electrons but by neutrons themselves, crushed together under immense pressure. Like white dwarfs, they cool over time, fading into cold, dark remnants. Some neutron stars may become black holes if they accumulate enough mass, but most will simply drift in silence, compact but inactive. In this era, the universe is not completely static. Remnants can still interact. White dwarfs and neutron stars may collide, merging into larger objects. Some collisions might trigger explosions, though these events will become rarer as time goes on, and objects grow more isolated in the expanding universe. Binary systems, where two remnants orbit one another, may slowly spiral together, releasing gravitational waves before merging. Occasionally, a black dwarf might be disturbed, reigniting nuclear reactions for a brief flare of light, though such events would be extraordinarily rare. The timescales here are staggering. The transition from white dwarf to black dwarf takes longer than the current age of the universe. We're talking about quadrillions of years, spans of time so vast that the mind can hardly hold them. And yet, given enough time, it is inevitable. All white dwarfs will cool, all neutron stars will fade, the universe will grow darker and darker, filled with degenerate matter that no longer shines. This era represents a kind of cosmic twilight. The structures remain, the planets, the remnants, the black holes, but the vibrancy is gone. Energy differences are smaller. Entropy has risen. Processes still occur, but slowly, quietly, in the background of a universe that is mostly silent. If you could stand in that time, the night sky would look nothing like it does now. No rivers of starlight, no galaxies glowing faintly. Only darkness, punctuated occasionally by the dim glow of a fading remnant or the flash of a rare collision. And yet, this age is not without interest. Physicists have suggested that black dwarfs, though inert, may eventually become the sites of exotic processes. Over vast timescales, some theories suggest that nuclear reactions could still occur through quantum tunneling, leading to occasional bursts of energy. These events would be incredibly rare, but they would punctuate the silence with brief flickers of light, reminders of the universe's former brilliance. The era of degenerate matter is also a reminder of how far entropy has carried the cosmos. Once, the universe was filled with hot plasma, glowing with energy. Then came the age of stars, where fusion burned bright. Later, the age of black holes, where gravity reigned. Now, in this era, the energy is mostly spent. The universe has become a place of leftovers, of remnants that no longer create but only persist. From a human perspective, it is almost impossible to connect with such a time. Our entire species has existed for only a fraction of the blink of an eye compared to these scales. Civilizations rise and fall in thousands of years, while the cooling of a white dwarf takes trillions. And yet, we are part of this story. The sun itself will one day become a white dwarf, and then a black dwarf, joining the ranks of degenerate matter. Our solar system, if it still exists, will drift in the darkness of this long era, silent and cold. What happens after the era of degenerate matter? By the time the last faint glow of white dwarfs has cooled into invisibility, by the time neutron stars have faded into cold silence, and by the time galaxies are nothing more than scattered remnants, the universe will have entered a new stage. It is a stage without starlight, without the warmth of suns, without the cycles of birth and death that once gave shape to cosmic history. What remains are the darkest and most enduring objects of all, black holes. This is the era of black holes, a time when the cosmos is dominated by gravity's most extreme creations, persisting long after everything else has gone. To see how we arrive at this point, imagine the long decline that comes before. Stars have burned their fuel, remnants have cooled, collisions have become rare, and matter has been slowly swallowed by black holes. In this landscape, black holes are the giants. They have already played a role in shaping galaxies, anchoring their centres and driving cosmic evolution. But now, in the absence of stars, they take centre stage. They are no longer hidden among billions of glowing suns. They are what is left. Black holes come in different sizes, but in this era, the largest ones will dominate. Stellar mass black holes formed from the collapse of individual stars will still exist, scattered throughout the darkness. But supermassive black holes, those millions or billions of times the mass of the Sun, will be the true monarchs of this age. They sit where galaxies once were, the remnants of galactic centres, having swallowed vast amounts of matter during earlier times. With galaxies faded and stars gone, these immense black holes will drift more quietly, but their presence will still shape the cosmos. Over time, black holes will continue to consume what remains. Any stray matter that drifts too close will be devoured. Stellar remnants, rogue planets, or smaller black holes that wander into their reach will be absorbed. Collisions between black holes will occasionally occur, merging them into larger and larger structures. Each merger sends ripples of gravitational waves across the universe, faint echoes of motion in an otherwise silent cosmos. These waves will carry energy outward, but in a universe that has grown cold and dark, they will be among the few remaining signals of activity. The era of black holes is not lively in the way the Age of Stars was. There are no bursts of starlight, no brilliant galaxies glowing against the void. Instead, it is an age of persistence. Black holes do not shine, but they endure. They sit in silence, invisible unless something falls into them, bending space and time with their gravity. In their way, they are the most patient actors of all, waiting as the universe ages around them. But even this era has an end. For a long time, black holes were thought to be eternal, perfect prisons from which nothing could escape. That changed with Stephen Hawking's discovery that black holes emit faint radiation. This Hawking radiation means that black holes are not permanent. They slowly lose mass, shrinking over vast timescales. The larger the black hole, the slower the process, but given enough time, even the mightiest will evaporate. During the era of black holes, this evaporation is mostly imperceptible. For a supermassive black hole, the timescale is so long that it dwarfs every other age of the universe. For quadrillions upon quadrillions of years they will persist, unchanged to any imaginable observer. But slowly, patiently, the process continues. Black holes lose mass particle by particle, photon by photon, their immense gravitational grip weakening as they shrink. The universe during this time will be almost unrecognizable compared to what we know. No galaxies, no stars, no planets, no visible light. Only black holes scattered across a vast, expanding darkness. Each one is a reminder of the cosmos's earlier richness, a remnant of collapsed stars and ancient galaxies. They will drift for unimaginable spans of time, occasionally merging, occasionally swallowing stray remnants, but mostly existing in quiet endurance. Eventually, the evaporation will become noticeable. As black holes lose mass, they grow hotter, radiating more quickly. For eons, their radiation is drowned out by the faint background glow of the universe. But as the cosmos continues to expand and cool, the background fades, and Hawking radiation begins to dominate. Black holes, once thought to be eternal, become temporary after all, their mass steadily trickling away. The smaller black holes will evaporate first, disappearing in flashes of radiation. Larger ones will linger, but even they cannot last forever. In their final moments, after untold ages of slow evaporation, they will brighten dramatically, releasing bursts of energy before vanishing completely. The universe will lose its last great structures, one by one, until only the radiation remains. The era of black holes, then, is both a time of endurance and a time of transition. It is the last age of structure, the final era when massive objects still dominate the universe. But it is also the prelude to the ultimate emptiness, the bridge between the fading of stars and the quiet uniformity of the dark era. Black holes, for all their might, cannot resist entropy's pull. They too will fade, leaving behind only a thin bath of energy spread across infinite space. It is humbling to imagine this time. The universe we know is vibrant with galaxies, brilliant with stars, alive with energy. To think of it replaced by a cosmos of black holes drifting in silence stretches the imagination, and yet it is part of the same story, the inevitable unfolding of the same laws that gave us starlight and life. The era of black holes is not separate from our world. It is its distant future, the long continuation of processes already at work. By the time the last black holes have finally faded into nothingness, the universe will have crossed into its quietest age. It will be a time without stars, without galaxies, without the brilliant structures that once defined the cosmos. What remains is a darkness deeper than anything we can imagine. A vast emptiness filled only with the faintest particles and radiation, spread thin across an ever-expanding space. This is sometimes called the era of darkness, and it represents one of the most desolate yet inevitable stages of the universe's story. To understand what this era looks like, imagine the long decline that has already taken place. First, there was the vibrant age of stars, when galaxies were bright with newborn suns and the night sky was alive with light. Then came the slow fading. As star formation dwindled, stars burned out and galaxies dimmed. After that, the remnants endured, white dwarfs cooling into black dwarfs, neutron stars fading into silence, and black holes dominating the cosmic stage. For trillions upon trillions of years, black holes remained as the last great structures, slowly evaporating through Hawking radiation. But even they could not last forever. When the final black hole vanished, the stage was empty at last. What follows is darkness. In this age, matter itself is sparse. Atoms, molecules, planets, and stars are gone. What lingers is a thin soup of subatomic particles, electrons, positrons, neutrinos, and photons, drifting endlessly through expanding space. The density of this cosmic soup is unimaginably low. The particles are so far apart that interactions between them are rare. For all practical purposes, the universe becomes static, not because nothing exists, but because what remains is so evenly spread and so low in energy that no meaningful changes can occur. This is the endpoint of entropy's long rise. In earlier times, entropy drove the flow of energy that powered stars' life and motion. Heat moved from hot to cold, light travelled across space, matter collapsed under gravity. But in this age, entropy has reached its maximum. Everything is uniform, balanced, and in equilibrium. Without differences in energy, nothing new can happen. The arrow of time continues to exist in theory, but in practice, the universe no longer has events to mark its passage. It's difficult to picture such a universe because it is so unlike our own. Right now, the night sky above Earth is filled with thousands of stars visible to the eye, and trillions more exist beyond our sight. Galaxies glow across the cosmos, and even the vast dark spaces between them are alive with radiation and activity. In the era of darkness, there is none of that. The night sky would not just be empty, it would be utterly blank, with no pinpricks of starlight to break the silence. If anyone could exist in that time, they would see only darkness stretching endlessly in every direction. And yet, the universe would not be entirely featureless. The faint radiation left over from the evaporation of black holes and from the decay of particles would still exist, but it would be spread so thinly and evenly that it would be nearly undetectable. Neutrinos, those ghostly particles that barely interact with anything, would drift endlessly. Protons, if they are stable, might still remain, though some theories suggest they may eventually decay too, leaving only lighter particles behind. Either way, the matter of this era is not the matter we know. It is not the rich structured matter of planets and stars, but a thin haze of the simplest particles scattered into almost nothing. The expansion of space continues during this age. Dark energy, if it remains as we understand it today, will keep driving galaxies farther apart, or what remains of them. But since galaxies are already gone, the expansion now acts on the diffuse particle soup itself. The universe grows larger, colder, and emptier with each passing moment. Distances stretch so vast that even the rare particles drifting in space are isolated from one another, never to collide or interact. In effect, the cosmos becomes a place of infinite loneliness, where each particle is cut off from all others by expanding space. The era of darkness is sometimes described as the final act of the universe, not because something dramatic happens, but because nothing happens. It is a state of quiet permanence, where the laws of physics continue to operate, but the conditions for change are gone. In this sense, it is not a finale but a silence, a universe that has run its course and settled into stillness. From a human perspective, it is tempting to call this bleak. A universe without stars or galaxies, without light or warmth, feels like an end stripped of meaning. But there is another way to see it. The very fact that we can imagine this distant future is remarkable. The laws of physics allow us to trace the universe's history across unimaginable spans of time, from the fiery beginnings of the Big Bang to the silent stillness of darkness. And in that story, our own existence is a fleeting but extraordinary moment. We live during the rare age when the universe is vibrant and alive, filled with stars and light. To know that this is temporary does not diminish it, it makes it more precious. The era of darkness may not be completely empty of mystery either. Some theories suggest that quantum fluctuations could still occur in this empty state. Tiny variations in the vacuum could, in principle, create pockets of new order, perhaps even new universes. Though speculative, these ideas suggest that even the deepest darkness may not be the final word. Physics leaves open the possibility that endings are beginnings in disguise. Still, from the perspective of what we know today, the era of darkness represents the ultimate outcome of entropy. A universe that once blazed with energy, structure and life will settle into equilibrium, a quiet bath of faint particles and radiation spread thin across infinite space. The brilliance of galaxies and stars will be long forgotten, their remnants evaporated, their light extinguished. What remains is silence, and yet silence has its own meaning. Just as the quiet after a song makes the melody more profound, the darkness at the end of the universe gives weight to everything that came before. The stars that shone, the galaxies that spun, the planets that carried life, all of it stands out more brightly when we realize that it was temporary. The darkness gives context to the light, reminding us that the universe's story, however long, is still a story with a beginning, a middle, and an end. Does the story of the universe end here, in silence and stillness? Or do the strange rules of quantum physics allow for something beyond, a flicker in the dark that sparks new beginnings? In the silence of the dark universe, when stars and galaxies have long since vanished, and even the black holes have evaporated, it might seem that the story has reached its quiet conclusion. The cosmos has run down, entropy has levelled out, and what remains is a thin, cold haze of particles spread across an expanding emptiness. It is tempting to think of this as the final state, a universe without events, without structure, without possibility. And yet, physics leaves room for something stranger. Even in a vacuum, even in what seems like perfect stillness, the quantum world is never truly quiet. At the smallest scales, fluctuations are always present, and those fluctuations could hold the seeds of something new. Quantum mechanics tells us that emptiness is not really empty. Space is alive with constant activity, particles flickering in and out of existence, borrowing energy briefly before disappearing again. This restless behaviour is built into the fabric of reality. It means that even in the most desolate phase of the universe, the Dark Era, activity continues on microscopic scales. The question is whether this activity could ever lead to something larger, something that breaks the silence of darkness and starts the universe's story anew. One idea is that, given enough time, quantum fluctuations could produce small but significant events, like the brief formation of particles or even entire structures. Most fluctuations vanish almost instantly, leaving no trace, but in theory, some could grow into something stable. The vast emptiness of the universe provides infinite time and infinite space for such fluctuations to occur. If the laws of physics allow it, then eventually, somewhere, a fluctuation could give rise to a pocket of order in the sea of disorder. This leads to the concept of vacuum decay. The vacuum of our universe, the baseline state of space, might not be truly stable. It could be a false vacuum, a state that appears stable but could, under the right conditions, transition to a lower energy state. If that were to happen, a bubble of this true vacuum could form and expand at nearly the speed of light, transforming the universe in its path. To any observers, the transition would be catastrophic and instantaneous, rewriting the very laws of physics as the bubble consumed space. In the distant future, such an event might be one way the universe finds a new beginning, though not one we could ever experience or control. Another idea is that fluctuations could create entire new universes. In some models of cosmology, tiny regions of space can undergo rapid inflation, expanding into full-fledged universes with their own space, time, and physical laws. In this picture, our universe might not be unique, but just one bubble in a vast multiverse, each bubble born from fluctuations in an eternal background. If so, the darkness of our universe might be less an ending and more a transition, the quiet after which other universes continue to bloom. These ideas are speculative, and much about them is uncertain, but they reveal something profound, that even the deepest silence of the universe may not be absolute. The rules of quantum physics leave open the possibility that endings are not final, that from the flat equilibrium of maximum entropy, new structures could emerge. The universe might not be a single story with a single ending, but part of a larger tapestry of beginnings and endings, woven together by fluctuations in the quantum fabric of reality. It is strange to think that the smallest scales could determine the largest outcomes. Quantum fluctuations occur at lengths far smaller than atoms, invisible and fleeting. Yet in some models, these tiny events can shape entire universes. The very existence of our universe might be the result of such a fluctuation. Perhaps the Big Bang was not a singular event, but just one instance of a process that happened again and again across the multiverse. If so, then the darkness of our universe is just one chapter in a story that stretches beyond our ability to see. From a human perspective, these possibilities are dizzying. We live in the middle of one universe during the age when stars and galaxies shine. To us, the idea that other universes might exist, or that ours could someday spawn new ones, feels almost unimaginable. And yet the mathematics of physics allows it, even hints at it. We cannot know for certain, but the possibility remains, and that possibility changes how we think about the end. If quantum fluctuations can give rise to new universes, then perhaps there is no final end at all. Perhaps the cosmos is eternal, not in the sense of one unbroken existence, but in the sense of an endless cycle of creation, each new universe born from the silence of the last. In that view, the darkness of our universe is not emptiness, but a womb, a place from which new beginnings may someday arise. Even if such beginnings are possible, they unfold on scales of time and distance so vast that they are forever beyond us. No civilization could endure long enough to witness them. No observer could survive to see the transition. These are not events for participants, but for the cosmos itself, the natural consequence of laws written into the fabric of space and time. From our perspective, the darkness is final, but from the perspective of physics, it may be only one stage in a larger eternal pattern. Thinking about these possibilities can be both unsettling and comforting. On the one hand, it means that the universe as we know it is temporary, destined to fade into silence. On the other, it means that silence may not be the end. The same fluctuations that shaped our world may continue to shape new worlds long after ours is gone. In that sense, the universe is never truly finished. It is always unfolding, always renewing, always beginning again. When we talk about the fate of the universe, it's easy to assume we're talking about everything. After all, the word universe usually means all of space, all of time, and all of existence. But physics has a way of challenging our intuitions, and one of the most surprising ideas to emerge in recent decades is that our universe may not be the only one. Instead, it may be just one bubble in a vast multiverse, a larger reality where countless universes exist, each with its own laws, histories, and possible endings. If that is true, then when we ask how the universe will end, we may need to widen the frame. The end of our universe might not be the end of everything. It might just be one among endless endings, each as real as our own, each unfolding according to its own rules. The idea of a multiverse arises from several corners of physics. One source comes from inflation theory, the idea that in the earliest moments after the Big Bang, space expanded at an incredibly rapid rate. This inflation smoothed out the universe, explaining why it looks so uniform today. But inflation may not have been a one-time event. In some models, it continues eternally, with different regions of space undergoing bursts of inflation at different times. Each burst gives rise to a new bubble universe, with its own distinct properties. Our observable universe would then be just one bubble among countless others, all floating in a vast, inflating background. Another path to the multiverse comes from quantum mechanics. In the many worlds interpretation, every possible outcome of a quantum event actually happens, with the universe splitting into multiple branches each time. If this interpretation is correct, then reality is constantly branching into parallel universes. Every choice, every random outcome, every fluctuation spawns a new world. In this view, the multiverse is not just a collection of distant bubbles, but an infinite branching tree of possibilities, all existing side by side. String theory, too, points toward the possibility of multiple universes. In its framework, the laws of physics depend on the shape of extra dimensions beyond the three of space and one of time that we experience. Different configurations of these dimensions could give rise to different sets of physical laws. If the universe contains regions where these configurations vary, then each region could behave like a separate universe with its own constants and particles. No matter which path we follow, the result is the same, the suggestion that our universe is not unique. If so, then the question of endings becomes even more fascinating. Our universe may fade into heat death, collapse into a crunch, or tear apart in a rip. But elsewhere in the multiverse, other universes may be ending differently. Some might be young, still filled with stars and galaxies. Others might be old, drifting into silence. Some might have physical laws so different from ours that they look nothing like the cosmos we know. Taken together, the multiverse is not one story, but countless stories, each with its own arc, its own conclusion. This picture changes how we think about finality. In a single universe model, the end is absolute. Once our cosmos reaches heat death or some other fate, that is the conclusion of everything. But in a multiverse, endings are relative. Our universe may end, but the multiverse as a whole continues. Somewhere, new universes are being born, expanding, evolving, and eventually ending in their own ways. The cycle of creation and destruction is endless, with no single final moment. It also reframes our place in the cosmos. If the multiverse is real, then our universe is one bubble among perhaps infinite others, not particularly special, except to us. The fact that our universe has the physical laws it does, laws that allow stars, planets, and life, might then be a matter of selection. In most universes, the laws may not permit such complexity. But in ours, by chance or by necessity, the conditions align to make life possible. This idea is sometimes called the anthropic principle. We observe this universe because it is one of the rare universes where observers like us can exist. From the perspective of endings, this means that even when our universe has faded into silence, the multiverse may remain lively. Somewhere else, stars may still be shining, galaxies still forming, and civilizations still wondering about their own fates. The end of our universe is not the end of all things, but one note in a symphony of countless universes playing at once. Of course, the multiverse remains speculative. We cannot see beyond the limits of our own universe, so direct evidence is lacking. The idea arises from mathematics, from extrapolations of known theories, and from attempts to explain why the universe has the properties it does. Some physicists embrace it as a natural consequence of our best theories. Others caution that without testable predictions, it remains philosophy rather than science. But whether or not it is real, thinking about it expands our imagination, reminding us that the cosmos may be far stranger than we can currently see. If the multiverse exists, it also opens new possibilities for beginnings. Just as quantum fluctuations could create new universes, eternal inflation might be generating them endlessly. In that case, there is no final end. Even if our universe drifts into darkness, the larger multiverse carries on, spawning new worlds forever. Time itself may be infinite, not for any single universe, but for the multiverse as a whole. Endings and beginnings occur endlessly, each universe a bubble rising and fading in an eternal sea. For us, though, the multiverse is more a thought experiment than a lived reality. We inhabit one universe, with its own history and its own fate. To us, the end is still final, because when our universe fades, it takes us with it. We cannot leap from one bubble to another. Our lives, our stars, our galaxies belong to this cosmos and no other. Yet in contemplating the multiverse, we glimpse a larger context. We see that even endings may not be absolute, that the silence of one universe may be counterbalanced by the birth of another. There is a certain comfort in that picture. The universe we know is temporary, but perhaps creation itself is endless. Perhaps the cosmos never truly stops, but always finds new ways to begin again. The multiverse offers a vision of endless endings, each one final to those within it, but never final in the larger scheme. And so, while our own universe may fade, the story of existence continues beyond it, beyond our sight, beyond our reach, but not beyond imagination. What if the universe itself is not just one cycle among many bubbles, but cyclic in its own right? What if expansion and contraction alternate forever, giving rise to new beginnings within the same universe, looping endlessly through time. For as long as people have wondered about the universe, they have also wondered whether time itself might repeat. We see cycles everywhere in nature: the rising and setting of the sun, the phases of the moon, the turning of seasons, the birth and death of living things. In these patterns, beginnings and endings are never absolute. Night gives way to day, winter to spring, life to new life. It is only natural to ask whether the cosmos itself might follow a similar rhythm. Could the universe be cyclic, expanding and contracting in endless loops, with each cycle giving rise to new beginnings? The idea of a cyclic universe has a long history. Ancient philosophers often imagined the cosmos as eternal and repeating, with no single creation moment or final end. In modern science, the concept re-emerged with the discovery of cosmic expansion. If the universe is expanding now, might it eventually slow, contract, and collapse in a big crunch, only to rebound in a new Big Bang? That would create a cycle, with each universe born from the ashes of the one before. Instead of a single line with a beginning and an end, cosmic history would be a circle, looping forever. One version of this idea is simple. The universe expands, collapses, and then explodes outward again, repeating the pattern endlessly. Each cycle might last trillions of years, with stars, galaxies, and life arising anew each time. In such a picture, there is no true beginning and no final end, only an eternal rhythm of birth and death. Our current universe would be just one cycle among countless others, not unique but part of an infinite sequence. But cycles need not be identical. In some models, each new universe might differ from the last. The conditions of the Big Bang could vary slightly, leading to different laws of physics, different constants, or different structures. If so, then every cycle would be unique, a new experiment in cosmic history. Some universes might be rich with galaxies and stars, others might be sparse, or collapse quickly, or evolve into forms we cannot imagine. The cycles would not repeat exactly, but would echo one another, variations on a theme. Modern cosmology has explored these ideas in various ways. Some versions of string theory suggest that our universe could be one cycle, in a repeating sequence of collisions between higher dimensional spaces, called branes. Each collision would trigger a new Big Bang, sending the cycle forward. Other models propose that the expansion of our universe might one day reverse if dark energy changes its nature, leading to a collapse and rebound. Still others imagine that quantum effects at the moment of collapse could create the conditions for a new expansion. These models remain speculative, but they offer a compelling alternative to final endings. Instead of fading into silence or tearing apart, the universe could renew itself endlessly. The arrow of time would still march forward within each cycle. Entropy would still increase. Stars would still shine and die. But at the end of each cycle, a reset would occur, and the story would begin again. The idea of cycles also changes how we think about meaning. If the universe repeats forever, then endings are never truly final. The death of stars, galaxies, even universes becomes part of a larger continuity. What seems like an ending from one perspective is only a transition in a larger rhythm. This echoes the patterns we see in nature, where death and rebirth are intertwined, where endings are inseparable from beginnings. Of course, cyclic cosmologies raise difficult questions. If the universe repeats, does it repeat exactly? Could there be another cycle where everything happens the same way, down to the smallest detail, including you listening now? Or does each cycle differ in ways that make exact repetition impossible? Physics does not yet provide clear answers. The mathematics of entropy suggests that exact repetition may be unlikely, since entropy increases in each cycle. To reset, the universe would need a mechanism to reduce entropy, something not yet understood. Without that, each cycle might be different, with entropy carrying forward, shaping the future in new ways. There is also the question of time itself. If cycles repeat forever, is time infinite, stretching endlessly through loops? Or is time an illusion of cycles, with each loop creating its own self-contained arrow? These questions blur the line between physics and philosophy, reminding us that our understanding of time is still incomplete. What makes cyclic cosmologies appealing is their symmetry. They suggest that the universe is not a one-way journey into silence, but a dance of expansion and collapse, a heartbeat of creation and destruction. They offer a picture where the cosmos never truly dies, but continually renews itself, always becoming, always unfolding. For some, this vision is more satisfying than a final heat death or a one-time Big Bang. It provides a sense of eternity, not in stillness, but in motion. At the same time, cyclic models are challenging to test. We can observe the universe's current expansion. We can measure the cosmic microwave background. We can study galaxies and stars. But evidence of past cycles, if they exist, is difficult to find. Each cycle may erase the traces of the one before, leaving us with little more than hints. Still, some researchers look for patterns in the cosmic microwave background, subtle imprints that might suggest echoes of earlier universes. Whether such evidence will ever be found remains uncertain. For now, cyclic cosmologies remain one possibility among many. They sit alongside heat death, the Big Crunch, and the Big Rip as visions of the universe's fate. Each possibility highlights different aspects of physics: entropy, gravity, dark energy, quantum fluctuations. Each tells a different story of how everything might end, or begin again. Thinking about cycles also leads naturally to deeper philosophical questions. If the universe repeats forever, does that mean everything is inevitable? Are we destined to live our lives over and over in endless cycles? Or does each cycle bring new possibilities, new variations, new choices? These questions remind us that cosmology is not just about distant galaxies and physics equations. It is also about our place in the story, about how we understand ourselves in relation to the cosmos. If the universe might loop forever, or if it might fade into silence, or if it might be one of countless universes in a multiverse, what does that mean for us? How should we think about our lives, our choices, our meaning in the face of such vastness? When we talk about the end of the universe, we usually imagine it in physical terms. Stars fade, galaxies dissolve, black holes evaporate, and eventually nothing remains but silence. Science offers us scenarios like heat death, the Big Crunch, or the Big Rip, each one grounded in laws of physics. But beyond the physics lies another layer of questioning, one that asks not just how the universe will end, but whether ending itself is a meaningful idea. If time stretches forward without limit, if cycles repeat, or if new universes can arise from fluctuations, then perhaps what we call an end is not truly an end at all. Philosophy has long wrestled with the idea of finality. Human beings are accustomed to beginnings and endings in daily life. Birth and death, sunrise and sunset, the start and finish of stories, all of these shape how we think about time. But when we try to apply the same categories to the cosmos, things become less clear. The universe is not a book that closes neatly when the last page is turned. It is an unfolding process, and processes do not always fit into simple boundaries of start and stop. One way to approach the question is to ask what we mean by end. Does an end mean the disappearance of all structure? If so, then heat death qualifies, because the universe loses all meaningful differences. But even in heat death, energy still exists, spread thinly across space. In that sense, nothing truly ends. It simply changes form. If matter and energy cannot be created or destroyed, then perhaps the universe cannot end in any absolute sense, only transform endlessly. Another approach is to consider time itself. An end implies that time continues up to a final moment and then stops. But what does it mean for time to stop? If there is no time, there is no change, and if there is no change, then nothing can mark the passage of an end. The concept dissolves. Some philosophers argue that asking about the end of time is like asking what lies north of the North Pole. It is not that there is something there, it is that the question itself may not apply. There is also the matter of perspective. To us, an ending feels final because it marks the conclusion of our experience. A person's death is an end to their story, even though the matter of their body continues in other forms. Similarly, the end of the universe feels final to us because it ends the conditions for observers like us to exist. But from a broader view, the cosmos may continue in ways we cannot witness or comprehend. An end may be an end only for us, not for existence as a whole. Religions and spiritual traditions have their own interpretations of cosmic endings. Some speak of apocalypses, of worlds consumed by fire or dissolved into nothingness, followed by renewal or transcendence. Others envision cycles of creation and destruction, where universes arise and dissolve endlessly. These stories often mirror the scientific models we now explore, but they focus less on physical processes and more on meaning. They remind us that the question of endings is not just about physics, but about how we as humans make sense of them. Even in secular philosophy, the end of the universe has been used as a backdrop for questions of meaning. If everything ends, does that make our lives meaningless? Or does it make them more precious because they are temporary? If the universe continues forever in cycles or multiverses, does that diminish the uniqueness of our lives? Or does it enrich them by placing them in a larger pattern? These questions are not answered by equations, but they matter deeply to how we think about existence. One perspective is that endings are necessary for meaning. A story without an ending is incomplete. A life without a boundary is not a life as we know it. By this view, the end of the universe is not a tragedy but a natural conclusion, the final chapter in a grand narrative. Just as the death of a star can create the elements for new life, the death of the universe may give context to all that came before. Another perspective is that endings are illusions. The universe is process, not product. What we call an end is only a transition from one state to another. Heat death, big crunch, big rip. All of these are transformations, not annihilations. Matter and energy continue, or new universes arise, or cycles repeat. By this view, the universe does not end any more than a wave ends when it returns to the sea. It is absorbed into a larger continuity. Still, another perspective focuses on the human side. Whether or not the universe truly ends, for us, the experience of an ending is real. Our lives are brief compared to cosmic timescales. For us, the universe has always been filled with stars, with galaxies, with light. We cannot imagine existing in a dark, silent cosmos. So when we speak of endings, we are also speaking of our own endings, projected onto the universe itself. The cosmos may go on, but our place in it will not. These reflections show that the concept of an end is slippery. Physically, it may mean silence and equilibrium. Philosophically, it may mean transformation, perspective, or illusion. Spiritually, it may mean renewal or transcendence. In every case, the word carries meanings beyond the literal. To ask whether the universe ends is also to ask what it means for anything to end. If the universe ends, what does that say about our own meaning? If everything we know is temporary, does that diminish us? Or does it give our lives a kind of significance that eternity never could? When we hear about the universe's possible endings, the scales of time and space involved are so vast that they almost escape imagination. Trillions of years for stars to fade, even longer for black holes to evaporate, and still longer for the last particles to drift into silence. Against such immensity, human life seems impossibly small. Our entire history as a species spans only a few 100,000 years. Civilizations rise and fall in mere thousands. A single lifetime is but a blink. Compared to the grand arc of cosmic history, we are dust on the surface of dust, carried along for a fleeting instant, and yet we still ask what it means to live in such a temporary cosmos. If everything ends, where does meaning come from? For some, the impermanence of the universe feels unsettling. We often seek permanence as a foundation for value. If things last forever, we think, then they matter. If they vanish, then perhaps they do not. From this perspective, the heat death of the universe or the collapse of all things into a crunch seems to rob existence of meaning. Why build? Why love? Why create if everything will eventually disappear? This line of thought is not new. Philosophers, poets, and thinkers across history have wrestled with it. Long before cosmology gave us scientific scenarios of cosmic endings, the awareness of mortality, of individual lives, of civilizations, of the universe itself has always been part of the human condition. But there is another way to see it. The very fact that life is temporary can make it more meaningful, not less. A flower that blooms for a day is no less beautiful than a mountain that endures for ages. In fact, its fragility can make it more precious. The same is true for human lives and for the universe itself. Knowing that everything changes, that nothing lasts forever, can sharpen our sense of wonder for the moment we have. If the stars will one day fade, how extraordinary that we exist now, in the age when they shine. From this perspective, meaning does not come from permanence but from presence. We find significance not in the guarantee that something lasts forever, but in the fact that it exists at all. The universe did not have to be this way. The laws of physics could have taken other forms. Life could have failed to arise. Consciousness could have never emerged. And yet here we are, living in a cosmos filled with stars and galaxies, able to look out at the night sky and wonder about its fate. That is meaning enough, not because it is eternal, but because it is real. Human meaning in a temporary cosmos also arises from connection. Even if the universe ends, the connections we make to one another, to nature, to the cosmos itself, shape our lives profoundly. A parent caring for a child, a scientist studying the stars, an artist capturing beauty, a community building together. These acts matter because they enrich the lives of those who live them. They do not need eternity to be significant. They matter here and now in the moment they are lived. The awareness of cosmic impermanence can also deepen gratitude. When we realize how brief and improbable our existence is, we may feel awe for the chance to be here at all. Out of billions of years of cosmic evolution, out of trillions of stars on one small planet at one fleeting moment, life emerged and consciousness arose. To exist at this intersection, to be part of the universe aware of itself, is extraordinary. The universe may not last forever, but the fact that it produced beings capable of contemplating its fate is astonishing. Some find meaning in imagining that their actions ripple outward, even if only briefly. A word of kindness, a discovery, a work of art. These may not endure for eternity, but they shape the lives of others, who in turn shape the lives of more. The chain of influence extends outward, like ripples on water, even if the water eventually grows still. In this sense, meaning is not measured in permanence but in impact. The cosmos may end, but within it, each life has the power to shape others, and that is a kind of immortality of its own. Others turn to philosophy or spirituality to grapple with cosmic impermanence. Some traditions teach that impermanence itself is the essence of reality, that clinging to permanence causes suffering, and that peace comes from embracing change. Others hold out hope for transcendence, for realities beyond the physical universe, for continuations that science cannot measure. Whether through acceptance or hope, these approaches remind us that human beings seek meaning, not only in facts, but in interpretation, in the ways we frame our place in the cosmos. Even science itself can provide a source of meaning. To know that the universe evolves, that stars live and die, that galaxies form and fade, is to participate in a story far larger than ourselves. We are stardust, as the saying goes, made of elements forged in the hearts of long-dead stars. Our bodies carry the history of the cosmos within them, the calcium in our bones, the iron in our blood, the oxygen we breathe, all were shaped in cosmic furnaces billions of years ago. When we reflect on the universe's temporary nature, we're also reflecting on our own origins. Meaning arises not from permanence, but from belonging to this great unfolding. The awareness of cosmic impermanence can also inspire creativity. Knowing that nothing lasts forever may push us to create while we can, to bring beauty, knowledge and kindness into the world. It may encourage us to cherish relationships, to care for the planet, to build societies that nurture life. These acts may not echo forever, but they shape the time we have, and that shaping is meaningful in itself. There is also the perspective that meaning is not given by the universe but made by us. The cosmos may not care whether we exist, but we care. We choose what matters. We give value to love, to discovery, to justice, to beauty. These choices do not depend on the universe lasting forever. They depend on us, here and now, deciding what is important. In this way, impermanence does not rob life of meaning, but makes meaning something we actively create. When we think of the universe's fate, we are reminded that we are temporary. Our species will not last forever, nor will our planet, nor will our stars. But that does not diminish us, it situates us. We are part of a cosmos in motion, part of a story that stretches across time. Our meaning comes not from outlasting the universe, but from participating in it, from living our brief moments fully and deeply. And so, as the universe moves toward its possible endings, we can reflect on our own. Just as the cosmos will transform, so will we. Just as stars fade, so do lives. But in that fading there is beauty, and in that beauty there is meaning. Impermanence does not erase significance, it creates it. When we look out into the night sky, we are not just seeing stars and galaxies scattered across space. We are seeing the story of the universe itself, written in light that has travelled for millions or billions of years to reach us. Each star is a reminder that we live in a cosmos that is vast, ancient and always in motion. And in that motion, in that unfolding, we find ourselves, a species on a small planet, orbiting an ordinary star, wondering what it all means. Our place in this great unfolding is at once humble and extraordinary. Humble because of our smallness, extraordinary because we are able to ask the question at all. Science tells us that the universe is about 13.8 billion years old. In that time, matter has gone from a hot plasma soup to stars, galaxies and planets. From simple beginnings, complexity has emerged, until eventually life appeared and consciousness followed. We are part of that chain, one outcome of billions of years of cosmic evolution. The same laws of physics that govern galaxies also govern us. The same atoms that form stars form our bodies. We are woven from the same fabric as the universe itself. This means that when we ask about our place in the great unfolding, we are not separate from it. We are the universe asking about itself. It is easy to feel small when thinking about cosmic scales. The Milky Way contains hundreds of billions of stars. Beyond it lie trillions of galaxies stretching farther than we can see. The distances are incomprehensible, the timescales overwhelming. And yet smallness does not mean insignificance. A single note is small compared to a symphony, but without it the music is incomplete. In the same way, our existence, brief and tiny though it may be, is part of the universe's song. Our place in the great unfolding can be seen through the lens of time. For almost the entire history of the universe, there was no life, no consciousness, no reflection. Only recently, on a cosmic scale, has the universe become aware of itself through beings like us. We are latecomers to the story, but that makes our role all the more precious. We live in the rare window when stars still shine, when galaxies are visible, when life can flourish. This moment will not last forever. Stars will fade, galaxies will dim, and consciousness may vanish. But here and now, we are part of something remarkable. A universe alive enough to ask about its own destiny. Our place can also be seen through the lens of matter. The atoms in our bodies were forged in stars that lived and died long before the Earth was born. The carbon in our cells, the iron in our blood, the oxygen we breathe, all were created in stellar furnaces and supernova explosions. We are literally stardust, assembled by cosmic processes over billions of years. To realize this is to see that we are not separate from the universe, but expressions of it, temporary arrangements of atoms that once belonged to stars and will one day belong to something else. Our place can also be seen through the lens of connection. Though we are tiny, we are connected to everything. The light we see from distant galaxies is connected to the fusion in their stars. The air we breathe is connected to the plants that release oxygen. The food we eat is connected to the Earth's soil, water, and sunlight. The gravity that holds us on Earth is the same gravity that binds galaxies together. In every direction, we are woven into the unfolding fabric of existence. Our place is not isolated. It is part of a web that stretches across space and time. Some people wonder whether our place has purpose. Does the universe have intentions? Are we here for a reason? Science cannot answer those questions. It shows us processes, not purposes. But perhaps purpose is not something given to us by the cosmos. Perhaps it is something we create within it. We give meaning to our lives by how we live them, by caring for one another, by seeking knowledge, by creating beauty, by building connections. Our place in the great unfolding may not come with a script, but it comes with the freedom to write one. At the same time, reflecting on our place in the cosmos can give us perspective. Many of the things that consume our attention in daily life are small compared to the sweep of cosmic history. The arguments, the worries, the ambitions, they matter in the moment, but they are not everything. To remember that we are part of a universe billions of years old can be humbling. It can remind us to step back, to breathe, to see our problems in a larger frame. That does not make them unimportant, but it can give us balance. Our place in the great unfolding is also a responsibility. We are the first species, as far as we know, to understand the universe's story. We can map the stars, measure the expansion, and imagine the future. With that understanding comes a responsibility to care for our planet, for one another, and for the fragile life that exists here. Earth is the only home we know, a rare oasis in a vast, mostly empty cosmos. To know our place is also to know our duty, to preserve it, to nurture it, to make it flourish while it can. Even though the universe may end, even though our time is brief, our place is still meaningful. Meaning does not require eternity. It requires participation. We are participants in the cosmos, not just observers. Every breath, every thought, every action is part of the great unfolding. The universe does not ask us to last forever. It asks us only to exist, here and now, for the time we are given. And so, when we reflect on our place in the great unfolding, we can see it as both humble and profound. Humble, because we are small and temporary. Profound, because we are connected to everything. Because we carry the history of the universe within us, and because we can reflect on it with wonder. That wonder is perhaps our truest place. The ability to look at the stars, to imagine their fate, and to feel awe for the fact that we are here at all. As we come to the end of this long exploration, it feels natural to pause and breathe for a moment. We have followed the story of the universe from its beginnings in fire and expansion, through the birth of stars and galaxies, through the slow dimming of light, and into the distant possibilities of heat, death, crunch, rip, and silence. We have looked at black holes lingering as the last great structures, at quantum fluctuations that whisper of new beginnings, at multiverses and cycles and philosophies of impermanence. Each possibility paints a different picture, but all of them remind us that the cosmos is a story with motion, with transformation, with unfolding, And now, here in these closing reflections, the focus turns not to endings, but to the feeling of resting in the infinite. Resting in the infinite does not mean knowing all the answers. It means allowing ourselves to sit with the vastness of what we do not know and finding peace there. The universe stretches beyond our comprehension in both space and time. Galaxies number in the trillions, stars in the countless billions, particles beyond imagining. Time stretches backward for nearly 14 billion years and forward into spans so long that words lose their meaning. To place ourselves within that frame is humbling, but humility can be restful. It takes away the burden of needing control, of needing certainty. We do not need to solve the infinite to rest in it. When we imagine the universe's fate, we're imagining events so distant that they dissolve any sense of urgency. Heat death, black hole evaporation, dark eras. These are not tomorrow's problems. They are not even the problems of the next billion tomorrows. They are possibilities painted across a canvas of trillions upon trillions of years. Knowing this can free us. The future of the cosmos is vast and slow. Our place within it is small and brief, and yet in that smallness we can rest. We are not responsible for the destiny of galaxies. We are responsible only for the moments we live. Resting in the infinite also means embracing impermanence. We often long for things to last forever, whether they are relationships, achievements, or even the universe itself. But impermanence is not failure, it is nature. Stars are born, they shine, and they fade. Planets form, they change, they dissolve. Civilizations rise and fall, lives begin and end. The universe itself will follow its course. To rest in the infinite is to see impermanence not as something to fear, but as part of the great unfolding. Endings are transitions. Silence is as natural as sound. Darkness is as natural as light. From this perspective, the future scenarios of the universe, whether silence, collapse, or renewal, become less about loss and more about flow. The universe is not something broken that needs fixing. It is something alive that changes. It is enough to witness it, to be part of it, to let it move through its stages while we live in ours. Just as we do not control the rising of the sun or the turning of the seasons, we do not control the fate of the cosmos. And just as we can find peace in watching a sunset or a cycle of spring and fall, we can find peace in knowing that the universe too has its cycles and sunsets. Resting in the infinite also involves wonder. For all the talk of endings, the most striking thing about the universe is not how it will fade, but that it exists at all. Out of nothing, or out of something deeper than nothing, arose space, time, matter, energy, and eventually life. That it happened is astonishing. That we can sit here alive and conscious reflecting on it is even more so. Wonder is the natural response to the infinite. It is not about solving mysteries, but about being present with them. It is about letting ourselves feel awe at the fact that the universe is here, and that we are here within it. In this way, resting in the infinite is not passive, it is active presence. It is choosing to live fully within our brief moment, not in spite of the universe's impermanence, but because of it. It is loving while we can, creating while we can, learning while we can. It is holding gratitude for the gift of existence, however temporary. It is shaping meaning not from eternity, but from immediacy. We are not outside the universe, watching from a distance. We are part of it, woven from its atoms, carried by its laws, unfolding with it in every breath. As we close, think of the night sky. The stars you see are ancient, their light travelling for years or centuries or millennia before reaching your eyes. Some of those stars are already gone, their light a message from the past. Others will shine long after you're gone. The sky is a reminder of both impermanence and continuity, of both smallness and vastness. To rest in the infinite is to stand under that sky and feel both humbled and comforted. Humbled because we're small, comforted because we belong to something vast. In the end, the universe will follow its path, whether to silence, collapse, or renewal. We do not know which, but we do know this: we're here now, part of the unfolding. That is enough. To rest in the infinite is to accept that we are temporary but real, fleeting but meaningful. It is to close our eyes not in despair but in peace, knowing that we are part of the cosmos and the cosmos is part of us. So let the infinite stretch beyond you. Let the silence of future ages be a comfort, not a fear. Let the impermanence of stars remind you to cherish the light you have. Let the unfolding of the universe remind you that you too are unfolding and that your place in the story, however brief, is irreplaceable. And now, as we bring this journey to a close, you can simply rest. Rest in the vastness, rest in the silence, rest in the infinite. The universe is still unfolding, and so are you. Thank you for joining me on this long journey through the cosmos. We've travelled from the birth of stars to the silence of black holes, from the possibilities of heat death to the mysteries of cycles and multiverses. And through it all, one feeling carries us: wonder. If you found this exploration soothing, I'd be glad if you chose to return here again. You can subscribe, share, or simply let this be a place you come back to when you'd like to rest and drift with the universe for a while. For now, you can close your eyes. Let your breath slow. Imagine the stars above you, glowing softly, ancient and calm. Know that you are part of the same unfolding story, brief but beautiful. The universe continues, and so do you for this moment exactly as you are. Rest well.